Welcome to APEC. It is Saturday, November 23rd, 2024, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. The last couple of weeks have been just crazy busy in a good way. We have accomplished so much stuff, and we hope to show you more of that in our lab updates today. But first, we do have some amazing presenters I'm really pleased to showcase for you. So starting right out, John Brandenburg is going to be presenting on the fine structure constant. Max Fomitchev-Zamilov will be discussing experimental bubble fusion research, and Eric Reiter will be presenting an overview of the threshold model. Now, Greg Hodgin was going to join us, but he actually has a family emergency, so he's not able to make it. So we will hopefully work him in the future for that presentation. And after that, we're going to be hearing updates from our lab partners, finishing off the event with an open discussion. Again, really, really exciting stuff. So today's event is on StreamYard. We are broadcasting through the Alt Propulsion YouTube channel. If you haven't subscribed, please do so now. You can also ask questions using the live chat feature on the right-hand side of the page, and we may drop links in there as well. So we're going to try and keep an eye on that, although it does scroll fast. We're not able always to get the correct questions out of there. So you can also view conference replays, details, and speaker info on our website at www.altpropulsion.com. So again, really, really excited. Last week, we were at Falcon Space doing the APEC 4th anniversary lab meetup, and I'm actually uploading that today as well. That'll be online later, so you can see that presentation if you missed it. So without any further ado, let me bring Mr. John Brandenburg in. John, welcome, sir.
Oh, Tim, it's such a great pleasure and honor to be on presenting here at APEC and to be on your site. You have enormously advanced breakthrough physics because of your forum.
We were before we started, you were trying to upload, I think it's the value of the quantum fine structure constant.
And the implications of that. Now, have you gotten that?
You know what? I can upload that for you. Yeah. So let me do that.
Oh, okay. Oh, you can. Good. Very good. Very good.
Yeah. Yeah. So what you'll have to do is give me the back and forth. Again, that's one of the limitations of it.
Sure, that's okay. I don't know why. Anyway. Okay.
Okay.
Here we go.
Yeah. So what I'm going to do, I'll hand this
over to you. This is the plain brown wrapper version. I had more pictures, but that for some reason won't upload.
Yeah.
Apparently.
Well, so I'm going to remove myself from it. I would say take it away and just let me know when to do next slide.
Okay. Say allow StreamYard to see your screen. Sure, it should be fine. Okay. What? Okay. I'm sorry. I thought this would all be very simple. Okay.
Yeah,
okay.
John, no, I think that's from I think that you still have the present button going there. I would just close that. I think that we're all set. Yeah.
Okay, great.
Yeah, just take it away and just tell me when next slide. So.
Okay. Okay, today I'll be discussing the value of the quantum fine structure constant, the derivation of that from first principles, and the emergence. What this leads to is apparently that quantum mechanics and time are both emergent from electromagnetism. So this is an important result, and I wanted to share it with everybody to get their take on it. Yes, please, next slide. Okay, in this talk, I'm going to be addressing two of the great mysteries of physics. One is the fact that despite the finest minds on this planet, we cannot quantize general relativity, Einstein's general relativity. My saying is, if Dick Feynman couldn't do it, nobody can do it. And the other great physics puzzle that we're confronted with is the sky everywhere we look is the same temperature. It's as though the photons from one end of the sky are meeting the other, and they're twins, yet their mothers never met. They've never met each other, and the universe seems to be, the Big Bang was thermally equilibrated, even though it was supposedly expanding faster than light. So anyway, I'll be discussing minimization of action and entropy production rate in the Big Bang. What are some of the founding principles of this universe when the Big Bang happened? I'll discuss electromagnetism and the emergence of time, and then the emergence of the action quanta H from the electric charge quanta E. And the space-time, I'll then go into, delve into a little abstract math. Space-time as a tesseract, a 4-cube. Derivation of the Wyler formula, a fellow named Wyler derived the formula for the fine structure constant. He was basically a mathematician, so he did it with very abstract math. People asked him, what is the physical meaning of this? He didn't know. And unfortunately, it apparently drove him to a nervous breakdown from which he never recovered. So we'll talk about the derivation of the Wyler formula from physical principles, especially the T to the fourth radiation law, the Planck radiation law. Then we'll talk about the implication of this is that electromagnetism is the foundation from which both time and quantum mechanics emerge. Then we'll summarize, and then we will briefly discuss the physical implications towards the two great questions I just mentioned of physics. Next. Tim, next slide.
Yeah, John, it should be the Big Bang, the first second. Is that what you're seeing?
Okay. Yes, I'm seeing. We're doing great.
Yeah, I think
I don't understand. By the way, I put this out on that.
Yeah, just slow bandwidth. That's all. So.
Okay. Well, I put this out on X. I was going to give this talk and what is it going to be about, and it generated a lot of interest. So it could be that a lot of people are watching this, which is good. Everybody should be watching the APEC conferences, Tim. So the Big Bang. Okay. The universe, we believe, began with a singularity and then expanded. Its initial expansion was faster than light. Then, of course, they've added this inflation model, all these things to try to explain what they see. Basically, the universe started out as nothingness, we believe, and then 1 second later, it was 99% hydrogen plasma. That is electrons and protons, two charged particles. And then everything evolved after that. Next. We're talking about the moment when kind of basically all physics as we presently experience it began. But what physical principles actually governed the initial instance, the initial very brief times, early times of the Big Bang? Well, we derive all of our laws of physics now basically from what's called minimization of action, Lagrange's principle. And action can be defined as either delta momentum times delta distance over which it occurs, or delta energy times delta time. These give the units of action. So the Big Bang would have to be governed by minimum action. You can derive the equations of general relativity for what's called Hilbert's action principle, and that gives you the equations of general relativity of Einstein. So now there's another principle that happens in addition to minimum of action. It's that entropy is produced at a zero rate in a lot of in transitions. Entropy starts at a zero rate and then proceeds at a minimum rate. A raindrop falling streamlines itself into forming a surface of minimum drag. If you drop hot water on a hot plate, it'll hover on a vapor layer. That's minimization of entropy. So we believe that would also occur in the first stages of the Big Bang. And as it turns out, this is completely consistent with the models of the Big Bang that we get from general relativity. Now, here's something interesting. You can define an action based on purely electromagnetic quantities. That's electron charge squared over the speed of light, which is determined by Maxwell's equations, which can also be derived from an action principle. So, if you're going to have minimum action, you would expect that the action associated with electromagnetism would appear first. Now, why this is an important statement is that H, the quantum of action upon which all quantum mechanics is based, is much larger than the electromagnetic action, which appears when you have charge and the associated fields of electromagnetism. Once you have charge and Maxwell's equations giving a speed of light, you can define an action. But it's basically independent of time. Speed of light is just a ratio of length to time. It has no evolution to it. But this is much, much less. It's less by a factor of 137, as it turns out, the fine structure constant, than H, or H bar, the quantum of action that runs quantum mechanics. It's like in a chess game. What is your classic opening? You start moving pawns first. You don't move the queen first. You move the pawns. If you're starting a poker game on Friday night in high school, what's the first ante? $1. Not $137. You start small. Now, the original universe was expanding based on our best models much faster than the speed of light. In a sense, you could say the universe was a bunch of electric charges, and in between them is space, and that space-time is expanding faster than light. So they don't see each other. They can't interact with each other. And because they can't interact, they can't scatter off one another, there can't be a second law of thermodynamics operating, because that's what creates entropy. And entropy creates time as we experience it. Time as we experience it is not just a coordinate we can move in wherever we want, like the rest, like X, Y, and Z. No, it advances because of the second law of thermodynamics. The second law of thermodynamics, entropy production with time, was not really operating when the Big Bang initially happened, you had a bunch of charges that couldn't interact because they're moving, the space between them is expanding faster than light. They can't talk to each other. They can't scatter off each other. They can't create entropy. So what that means is that time is, as we experience it, with an arrow, is emergent. And I'm going to show you that quantum mechanics emerged with time. So we had minimization of action, beginning with charges, the first ante in the big poker game, the first movements of the pawns in the great chess game, and then we had minimum entropy production. Soon as you develop your chess game and you open things up, you don't send your queen out to do battle initially. No, you have the pawns do that. You start small, not only with action, but also with entropy production. So next slide, please. Minimization of action is the foundation of all physics. That's where you can derive Newton's laws and quantum mechanics and general relativity for minimum of action. Now, if you're going to start small, if you want to make things small, you start with electromagnetic action. Charges over the speed of light, Maxwell's equations. And once you have Maxwell's equations, then you have Minkowski spacetime. But time is reversible. You can move freely in time, just like you can in X, Y, and Z. But it's only when the second law of thermodynamics kicks in that you can no longer move backwards in time. You're moving forward in time in a sheet. Now, if you have superluminal expansion, the charges can't see each other, they can't interact, you have no E&M radiation because the particles are either stationary or, depending on your frame of reference, moving in uniform speed at straight lines. No E&M radiation is produced. Nothing to quantize there in terms of what's going on. Next slide, please. All right. If you have superluminal expansion in the first parts of the Big Bang, you can't have entropy production. The particles can't see each other to interact. Entropy determines the arrow of time, the second law of thermodynamics. Entropy cannot be created, it cannot increase in time, and therefore time itself, as we experience it, with an arrow, does not exist. It emerges when the expansion of the universe slows down to light and then finally sublight. The particles can start interacting with each other through electromagnetic fields, and that's when entropy production begins and time's arrow is established. Next. Electromagnetic entropy is what determines the Planck spectrum. The invention of Max Planck, that's how quantum mechanics was invented. This is what tells you there's color temperatures. If you have a piece of hot iron, it can be white hot, it can be yellow hot, it can even be blue hot, it can be red hot, or in fact, it can just radiate infrared at even lower temperatures. So the transition is the black iron, the piece of iron is only radiating infrared when it's at lower temperatures. It finally turns red hot. You can see it. It turns yellow hot. Finally, white hot. And that corresponds to increases in entropy. Now, next slide, please. The emergence of time's arrow, as I've discussed earlier, only happens after the Big Bang slows down through luminal to subluminal, so the particles can start interacting with each other. Otherwise, every particle considers that it's the universe, and they're moving in a uniform rate. There's no acceleration of charges. That means no radiation in Maxwell's equations. No radiation, no quantum mechanics. Time emerges once you have the slowing down of the Big Bang. Next. Okay, as we all know, entropy increases in time. It also increases with temperature. However, the early Big Bang, you'd think, how can it have a temperature? Everything's moving faster than light. They don't even see each other. But as it turns out, by the time it becomes expansion at luminal and subluminal velocities, it's apparently already born with a temperature. Interesting. It's born with a temperature. Next. Quantum mechanics emerges from electromagnetism. Charged particles interacting, creating radiation and entropy, time, as we experience it. Not time in a Minkowski sense where you can move wherever you want in time, just like X, Y, and Z. No. Time is in the rent is due, friend. Time, the fine structure constant, means that charge quantization precedes action quantization by action minimization principle. The universe starts small, not just in terms of entropy production, but also in terms of action. Finally, charge does not require time for its definition, but action, as in H, does require time. Next. Here we go. This young lady is getting herself all charged up. But as long as she keeps her hand on that charged object, she's going to stay charged. Charge is independent of time. It's a constant. As opposed to action, here by a hot fuel dragster. Now that's action. That requires time. Time to 60 miles an hour in the case of a dragster. Next. Now I'm just going to make a brief digression on how we represent space-time and what it means if we have a Minkowski, if we have a three-dimensional object that's moving forward in time. And what does that create? Well, it raises its dimensionality. A moving square sweeps out of 3 cube in time, just a regular cube. And you could say, okay, the lengths of the sides is like 1 light second. That's basically the distance to the moon. Okay. How long, how wide is it? How deep is it? Or, how wide, how deep, how tall? 1 second, 1 light second. How far is it in time? 1 second. And what that means is it's no longer a 3 cube, it's a 4 cube, a tesseract. Next slide. Now, what happens? How do we experience this? Since we can't actually even visualize, because of our Darwinian programming, we didn't need to, that how can you visualize time as a fourth dimension when in fact we experience it as basically a moving sheet? Well, for example, if you have a cube, a three-dimensional cube, you can unfold it into six squares, two-dimensional cubes. So a 3 cube unfolds into 6 squares. It turns out a tesseract, a 4 cube, unfolds into 8 3 cubes. So like a cube has a surface area, and that's 6 times its volume to the 2/3 power. And a tesseract has a surface volume, what you experience as a volume in 3 space, and that's 8, the number 8 times the 3/4 power of the volume of the 4 cube. Next. So yes, the surface volume of a tesseract is 8 times the length of its sides to the 3rd power. If it's a 4 cube that is one light second in dimension, height, width, depth is all 1 second. Its duration is 1 second. Then when you find out what is the volume that this defines, it defines 8 times the volume of 1 light second cubed. Next. Now we get to the heart of the matter. Recently, I became obsessed with the problem of the fine structure constant. I'm following in the great tradition of Wolfgang Pauli, the invention of the Pauli exclusion principle, for which he got the Nobel Prize. He was so obsessed with the number 137 that he sought psychiatric help from none other than Carl Jung, who was very worried that he was headed for, as he Jung wrote in his diary, "I'm afraid he's headed for the loony bin." So the physical derivation, as it turns out, of the Planck T⁴ radiation law yields an alternative form that agrees to 1 part per million with the standard form. And that uses just fairly standard plasma physics plus the idea of radiation, that the interface, the radiating interface must be in radiation pressure equilibrium in addition to power balance, and charge quantization. Now, I presented this paper at the APS meeting in Arcata, California, a couple weeks ago as a poster. It's well received. And you can find a document describing this derivation in detail. It's quite detailed on ResearchGate. I'll give you guys the, I'll make sure that you guys are aware of the of that document so you can access it for yourself. Okay, the derivation assumes electric charge quantization, multi-particle interaction physics through electromagnetism, and radiation pressure equilibrium, and of course, power balance. And here's what it produces. Next slide, please. One gets an alternative expression for the T to the fourth Planck radiation law, and which is the Stefan Boltzmann constant times T to the fourth is the radiation rate from a surface at a certain temperature T to the fourth, temperature T. And you can see that the difference between these two alternative forms is one has, the standard form has 2/15 times pi to the fifth. The new form has 3 pi over 80 alpha to the 4/3 power. So you can simplify that, taking the parts of the formula that are the same and canceling them. So you just get two pure numbers related. And when you do that, you find out, you solve for alpha, or in this case, alpha to the inverse of alpha, 137. And you find you get what is called the Wyler formula, derived by Wyler purely mathematically in 1969. And it's good to within half a part per million with what is measured in the laboratory as recorded on co-data. And it says that the inverse fine structure constant is basically a geometric and numerical relationship that's actually, I mean, uses pi and a bunch of numbers, a bunch of integers to the 3/4 power. And what this says, next slide, please, is that the relationship between electric charge quanta and H, the quanta on which quantum mechanics is based, is basically just a geometric factor. This confirms Einstein's suspicion that geometry was what ran the universe, plus charge, as it turns out. Charge and geometry is what runs the universe. Quantum mechanics emerges from that, along with time as we experience it. Now, I'm just going to show you some formulas that come from the GEM theory, gravity electromagnetism theory. I mean, the idea that you can unify gravity and electromagnetism, which was Einstein's great quest. As it turns out, the mass of the neutral pi meson can be found to within a part per thousand using this formula. Now, this formula involves the fine structure constant, but it's really basically the relationship of H to the electric charge. And you can view it as the neutral pi meson is an excited resonance on a classical particle surface, ejecting a quanta. Next, please. Now, you can use this result to calculate the proton mass. If those of you who are familiar with the GEM theory know that the central parameter in the relationship between gravity and electromagnetism is the ratio of the mass of the proton to the electron, or roughly the square root of it. And as it turns out, the ratio of the of the mass of the protons to the mass of the electron is given to 17 parts per million by what's called the Lenz formula. It's 6 times pi to the 5th. It's entirely geometric. The proton and the electron are related through just geometry somehow. Actually, they're related through Planckian physics. Next phase, please. Now, if we take this pi to the 5th power, 6 times pi to the 5th power, and include it in our formula, recognize that pi to the 5th, in the fine structure constant, we find everything, the relationship between quantum mechanics and electromagnetism is mediated by a very geometric factor, 6 times pi, which is also the relationship of the proton to the electron. Think of the proton as a sphere the same size as an electron, full of 3 modes, 3 Planckian modes, which have a temperature of the pi meson mass, the neutral pi meson mass. Now, you have this exact formula, but since 42.85 is almost 45, you can actually simplify this if you sacrifice a little bit of accuracy. And as it turns out, the Planck constant, or Planck action, or you could call it the Planck charge squared, h bar times c, is, to within a few percent, 8, the surface volume of a tesseract. Tesla, Freudian slip there. Nikolai Tesla is lurking in the background, smiling, I believe, as we're having this discussion. And it's a volume of this magic number 42.85 to the 3/4 power. In other words, you have a a tesseract of volume 42.85, and you take the 3/4 power of that to get its surface volume times, which is then times 8. And as it turns out, Planck's constant is basically based on the surface volume of a tesseract times the electric charge squared. So the action quanta of quantum mechanics is a derived quantity, an unfolding tesseract of volume sigma. Quantum mechanics emerges with the birth of the proton. So when the proton-electron mass ratio was determined, protons were born out of an electromagnetic spectrum, which had a temperature of a pi meson, a neutral pi meson rest energy, which depends on alpha, but now we know that alpha can be derived completely from electronic charge. The proton emerged, and with that was when the quantum mechanics as we experience it was born. And that's why the sky is all the sky is the same temperature, because the mass of the proton represents a temperature. Once there were protons, every proton in the universe had the same temperature internally, and that's what determined the temperature of the Big Bang at that point. And even though they were, most of the universe was not talking to any other part of it, they all got the same temperature because it was hardwired into the properties of the vacuum from general relativity and electromagnetism. Next phase, please. In summary, minimum action principle leads to appearance of quantized charge before quantized action. Charge does not require time to exist, but quantum mechanics does. The early plasma has no particle-particle scattering interactions because it's expanding faster than the light. No radiation, no entropy, no quantum mechanics, as we based on H. The superluminal expansion of the early fireball and quantization of charge leads as the expansion of the universe to light and then sublight leads to the emergence of time and quantum mechanics. Now, what are the physical implications of this? Next. Trying to quantize general relativity has proved to be very frustrating. You can do it for very weak gravity fields. You can do the same thing with sound waves in a crystal. But the sound waves in a crystal they're quantized, but they're nothing fundamental. The crystal's interacting with a bunch of electromagnetic interactions, basically. And not only that, the structure of the crystal means there's a hard cutoff for the spectrum. You can't do quantum mechanics out to umpty-ump orders in a crystal because that way there's a cutoff. By something similar, the existence of black holes. If you have an uncertainty principle that says change of energy times change of time, what happens if you can't define time changes over the surface of a black hole where tidal forces go to infinite? In a sense, the inside of a black hole is no longer causally connected to the outside of the black hole. And that means you can't do quantum mechanics across that interface. You can't do it. Delta momentum times delta distance, you can't define the distance across the, yet falling into a black hole is easy. It's just like jumping off a roof. Physics is continuous, but quantum mechanics can't be. That means, Feynman tried to quantize gravity and failed. If Dick Feynman can't quantize gravity to all orders, like he did with electromagnetism, it can't be done, in my opinion. To me, trying to apply quantum mechanics as we understand it, which is an emergent thing, you're trying to apply emergent rules to something that is primordial, foundational. It's like sitting down for a bowl of nice vegetable beef stew and then asking, where's my salad fork? You're asking the wrong question. You got a spoon there, buddy, and a napkin. Eat up. Next phase. Now, this theory that quantum and time are emergent, basically quantum mechanics was born, the electromagnetic field, once it became basically luminal and protons assembled themselves, that's when the temperature, that determined the temperature of the whole body of the, that determined the temperature of the universe. The proton is hot internally. It's a bunch of quarks jumping around in there. They're hot. The electron is cool. That temperature of the inside of the proton is what determined the global temperature of the radiation fields during the Big Bang after, something like one nanosecond or something. This explains why the temperature of the sky is the same to within 100 microkelvins all across the sky. You have two photons meeting, and they're like twins. But they've never met, and their mothers never met. How could they be twins? But they are. That's because the initial temperature of the proton, when the proton formed in the gem theory, it was hot. And that heat was determined by global physics that applied everywhere instantaneously. And so that initial temperature of the Big Bang was hardwired by the properties of electromagnetism and the vacuum. So that's why the two twins are twins, even though they never met, their mothers never met, neither did their grandfathers. So that's the other implication. So I believe that ends my talk. Thank you so much for your attention.
John, you the man. You the man. Okay, let me take your slide share down. Okay.
Hey, I'm just doing my job here. I'm just doing my job.
let me bring everybody in here. Let's give Dr.
Right.
John Brandenburg an enormous
Thank you so
applause.
much, you guys. Thank you so much for listening to my talk. And yeah, I mean,
no, it's wonderful, man. That is wonderful. And let me apologize for the pre-holiday chaos, right? We're in like that final stretch. It's Thanksgiving week, and then we're going into Christmas meltdown after this, right? So,
absolutely. The holidays are closing in.
Yeah, absolutely. Absolutely. And I love the way that you derived that. And I love the way that you were able to explain all of that in the context of gem theory. So that's absolutely wonderful.
I was just obsessed with it. And now I know what Wolfgang Pauli went through. For about 2 months, I was obsessed with this derivation. And I must have filled 3 notebooks with scribbled equations, and then it suddenly all came out. It's a miracle as far as I'm concerned.
Oh, that's awesome.
And it agrees within a part per million, half a part per million with what they measure. That's the miracle.
Well, so let me ask if anybody, do any of you guys have questions for John? Anybody have questions?
Yeah, I've got a quick one. So if time is emergent at the start of the universe and then also stops working at the surface of the black hole, then why not say the universe is inside a black hole or something? or maybe it is.
Oh, well, I've never been inside a black hole. If I had been, we would not be having this conversation, because once you go in a black hole, that's a one-way door.
Well, so is time.
Yes, it is. Yes, it is, Mike.
I remember hearing about.
I argue that those two facts are well connected, and reversible physics is what we kind of all enjoy. But my coffee's getting colder as I'm sitting here looking at the cup, and I can't make it warm. It's not going to become warmer again unless I put it in the microwave. It's some things are, I'm sorry, reality's a bitch. One of them is, if the rent is due, don't tell your landlord. Time is an illusion. He said, "Where's my money?" You say, "Money is an illusion too." He says, "Okay, give me some illusion." So, no, Mike, your point is very well made. At the black hole, a lot of physics that we understand goes away. It's gone.
Well, so
in fact, they say the black hole has the black hole has no hair. I'm sorry, Tim.
Oh, so John, I've read at least hypothesis about if you create black holes or micro black holes, that at some point they might be able to seal themselves off from this universe, and there was a hypothesis that might create a new universe for each one, right? And they would be completely sealed off
Yes.
from ours. So, yeah. So
Yes,
in that,
they're not talking to each other.
yeah. But what's interesting about that is, even though you would say, well, our universe is big and those are small, apparently, if I remember the hypothesis correctly, it's relative to the size of the universe. So it doesn't really matter
Yes.
how, yeah, they would all be kind of the same size. So a new Big Bang, right? Every time you create.
Absolutely. Remember, this universe began small. We were talking small. I mean, the poker game did not start with $137 antes. It started with $1.
Yeah.
I survived many a great poker games in my senior year of high school.
So a follow-up question then. Can we play a prank on another universe and draw graffiti on the surface of the black hole? Like just put a bunch of matter in the specific spots and make their background.
I would encourage you to do that, but unfortunately they can't return the favor. You can curse the people inside the black hole all day. They can't curse you back. But then again, somebody from the outside of, the surface of the universe is a black hole. You can do the equation, you can do the derivation. That's the edge of the observable unit. If you want to know what life in a black hole is like, we're living in one, apparently, according to general relativity.
Now, so this would be this is kind of more of a philosophical thing, right? But when you're talking about upper and lower level universes, this goes back. I read a book, I believe it was called The Philosophy of the Matrix, and they really tackled this stuff during the virtual reality. When the Matrix came out, and people were starting to ask, okay, simulation theory stuff. And a very good philosopher made a point in that book. He'd said, if the universe that you live in, right, be it a simulation or inside of a black hole or a parent-child universe, anything, he said, if it is as real as the top level, then you should consider them to be parallel universes. So maybe that's how parallel universes work. Maybe that's maybe that's Copenhagen right there.
I mean, by the way, just because I am now saying that quantum mechanics is emergent does not mean it is not operative as a fundamental law of physics in the universe we experience. Just like the fact that time, I mean, The universe is still expanding. You could say, how do I know time is not an illusion? Well, look at the galaxies. They're moving farther away. The same goes for quantum mechanics. It's now a law of physics. It is a law of physics, just like the second law of thermodynamics. Just why the fact that my coffee is now cold, because I didn't drink anything during the talk.
I guess there's one more follow up to that. John Bush, he did a presentation a while back about a fluid dynamic model of quantum mechanics.
Yes.
With the emergent idea, are you kind of suggesting that there's some chaotic fluid dynamic nonlinear interpretation, which gives us the statistics of quantum mechanics, and it's emergent in that sense, maybe?
Oh, I believe that. My model is like the specific heat of a crystal can be derived using quantum mechanics, because the sound vibration spectrum, the thermal vibrations, follow a Planck law, but they're cut off at some level. I mean, you can't go out shorter and shorter wavelengths, because finally you get to the space between the atoms in the crystal, and you can't go any further than that. And so you have to cut off the spectrum, and otherwise you would get black holes in crystals. It's a I did that answer your question?
Not particularly,
I'm sorry,
but for another time.
Well, Michael, a wise man once said, "It's turtles all the way down."
Maybe.
I love that answer. In fact, the story version I heard, it was an old lady. It was an old lady who listened to a lecture about the universe in Britain.
It's interesting. We may hear as quantum computing moves forward. I've heard speculation that might be connected to many worlds, and so maybe we'll learn more about this from the physics of quantum computing.
Is it the red pill or the blue pill, Tim?
Well, take both just to be sure, right?
Take both just to be careful. Yeah. It's and I noticed David Chester is here.
Hey, how's it going?
Hey, Dave. I'm honored you would take in this presentation. And other questions?
Yeah, well, and we're actually at the top of the hour. So what I want to do is,
by the way, we got to go to our next speaker. You guys have been so kind. Thank you so much.
Well, John, thank you.
By the way, I have to be on another talk show. This one about UFOs.
Okay.
In about an hour, so I'm going to have to fade out after about another half hour. I apologize for that. I would like to be around. Oh, Bob Lazar has favored us with a comment. I like turtles. I do too.
It may not be the real Bob Lazar, but guys, let's put our hands together.
That would be
one more time for Dr.
Maybe
John
it's actually Bob Lazar all the way down.
Yeah. Thank you so much, you guys. Yes, and let us now look forward to our next thing on fusion energy. There.
Awesome. John, thank you again. Okay, and I'm just taking everybody out except for Dr. Max Fomitchev-Zamilov. Max, welcome, sir.
Hi, Tim. Thank you for having me.
Yeah, no, so we did, the folks listening may not know, you and I did a podcast interview a few weeks ago, and the work that you're doing is absolutely brilliant. So I'm so pleased that you're able to present for us.
You're very kind.
I have your original presentation. Did you want to try and upload that? Oh, you did? Okay.
Yeah, it's there.
Perfect. And let me see. Yeah.
Okay, I can navigate. Yeah, I see. I can flip pages. All right.
Perfect. Okay, well, I'm going to take myself out. And again, thank you so much. I think
Well,
the
thank
work
you.
that you're doing is absolutely brilliant. And this is, so this is energy related, I guess, but that's something that we feature on APEC and we're trying to do a little bit more of. And again, you're way out in front of the area there. So
Thank you. Well, once again, my name is Max Fomitchev-Zamilov. I'm the founder of Maximus Energy Corporation. And today I'm going to talk about my fusion work, but the official title is The Observation of Neutron Emission During Acoustic Cavitation. Because, and you'll learn about this in just a moment, I don't really know if I accomplished fusion, but I have observed neutrons. And usually neutrons mean fusion, but not always. And I will, discuss those points in just a moment. For the past 3 years, I've been working on bubble fusion. And some of you may know that bubble fusion means a version of inertial confinement fusion. And you know that broadly thermonuclear fusion falls into two categories. We have inertial confinement and magnetic confinement. So in magnetic confinement, we have large setups that involve tokamak type reactors where magnetic field holds plasma together. And in inertial confinement, you are talking about using pressure to keep plasma from spreading and flowing apart. And normally when we talk about inertial confinement fusion, we think of National Ignition Facility. So in a National Ignition Facility, we have hundreds of lasers that focus their light on a solid deuterium tritium ice pellet. So it's a cryogenic pellet about a couple of millimeters in diameter. So these laser beams illuminate that pellet, and the outer layer of the pellet evaporates at supersonic speed and launching a shock wave. In fact, a series of shock waves that converge at the center of the pellet. And if everything is done right, then a meaningful amount of thermonuclear fusion occurs in that pellet. And I think recently they reported that they observed for the first time ever fusion yield in excess of the energy that came into the pellet. It doesn't mean that this whole system was energy producing. They're saying it's just whatever energy went into this pellet, which is maybe 1% of the energy that is required to run the lasers, and that pellet produced maybe like 20 or 30% more energy. I don't remember, the exact figure. But it's far from being energy producing, and it's a very expensive installation with a bunch of lasers, so hundreds of PhDs and hundreds of billions of dollars are necessary. So I prefer, something simpler, and bubble fusion seems simpler. And here the idea is that bubbles are naturally spherical. So when they expand and collapse, they naturally maintain their spherical shape. And therefore, if you get your bubble right, and if you get your acoustic pressure right, basically your sound pressure right, so you can perchance make this bubble collapse so violently to where inside plasma heats up to thermonuclear temperatures. So if you fill bubble with deuterium, perchance you will get deuterium fusion. So this idea is not new. It's been tried by Telyarkin before, and he reported famously in Science. But unfortunately, a scandal ensued, and his work was therefore, I wouldn't say debunked. It was just scandalized enough to where nobody would touch it. It was a 10-foot pole. But because my background is in ultrasonics, I figured this is something that I understand better than anything else, and maybe I can get it to work. So this is what I set to work on in earnest about 3 years ago. And very quickly I realized that bubble fusion only superficially appears easier or simpler than inertial confinement fusion, because at the end of the day, bubble fusion also suffers from instabilities. So it's difficult to make bubble expand and collapse spherically. Rather, I can put it this way. It's easy to make bubble expand and collapse spherically as long as your driving pressures are very mild. But as soon as you are starting to compress the bubble harder and harder and your pressure goes up, bubble develops instability. So the same problem occurs as in inertial confinement fusion. Whenever you concentrate energy, instability always develops and bubble deforms. And here is a good illustration of how the deformation occurs. Basically, bubble develops a jet, and that cavitation jet impacts on whatever surface. Maybe it impacts on the surface of the vessel where this bubble is floating, or maybe on another bubble. So bottom line is, it's difficult to maintain for a bubble spherical shape when you need to achieve this colossal 1 to 1000 expansion ratio. So it's sort of, back to the same problem. But nonetheless, I decided I'm going to try and do it anyhow. And what you're looking here is a picture of my reactor. So that's the reactor that, you can sort of see on my background. So I'm still operating, the version of this reactor. But this is the reactor I've built for this bubble fusion work. And I'll show you another picture that's easier to comprehend. It's less cluttered. So in the center, you see my main reactor vessel, which is a 6-inch stainless T. So it's a vacuum T that's filled with mineral oil. Because I'm working with bubbles, I'm working with the fluid. So my fluid is mineral oil. It's multitherm IG4, basically vacuum oil. And inside that oil, I create microscopic or nanoscopic deuterium bubbles. So these bubbles are injected through the circulation loop that has a Venturi nozzle that's hooked up to a deuterium lecture bottle. And this is a circulation pump that feeds it. And behind this, you cannot see it really, it's because it's under the table. It's an ultrasonic driver that sends acoustic waves inside my reactor chamber. And here is my vacuum pump, and on the back is my laser diffraction system that I use to measure the bubble size distribution. But let me walk you again through this. So here is a schematic diagram. So my reactor is about halfway filled with oil. There is an ultrasonic driver at the bottom. It's connected to Branson Sonifier 550 power supply. So all of the components are off-the-shelf components pretty much. So this is my circulation loop that occasionally goes through a Venturi that formulates bubble. Sometimes I use oil filter to remove particulates. Sometimes I use a secondary cavitation chamber, but it's not terribly important. What is important is to monitor sound. I have a PCB piezoelectric transducer that's connected to the scope to read the form and intensity of the acoustic waves. And of course, to detect my neutrons, I use helium-3 tubes, neutron counters. So here's a close-up picture at my reactor. You can see that oil here looks cloudy. It looks cloudy because there are a bunch of tiny, microscopic deuterium bubbles in it. And out here, oil is of different color because this oil is not just oil, it's a suspension, it's rather emulsion of heavy water droplets in oil. And you can see that the reactor glass cracked. It's, one of the things I've learned and managed to produce is super, super strong acoustic waves that originate from expanding and collapsing water droplets suspended in oil. And those acoustic waves were so strong on more than one occasion, they broke up, this viewport glass. But more on it in just a moment. So I will start, first with, whenever you conduct a nuclear experiment, you're always looking for a marker. And I would argue that at this stage, it's too early to talk about any kind of excess heat in any kind of nuclear experiments. So be that National Ignition Facility or ITER or something else, nobody's measuring heat. Everybody's measuring some nuclear radiation, be that gammas or neutrons. And if you talk in fusion, everybody measures neutrons because if you count your neutrons, you can tell how much of fusion took place, and therefore you can extrapolate how much energy was produced. So nobody measures excess heat. Everybody measures neutrons, and whoever measures excess heat, I remain extremely skeptical of that. So tool of the trade is neutron. And here you see is helium-3 proportional counters that are combined in a bank of 6. So more counters, higher neutron count, higher sensitivity. That's why I use this. I used this neutron bank. And what you see here is the thermal neutron spectrum. So I'm counting thermal neutrons. So neutrons pass through oil and they thermalize. And once they're detected by helium-3 field proportional counter, you're supposed to see this rather characteristic thermal neutron spectrum. So this is how I know that I'm counting neutrons and I'm not counting noise or gammas or something else. Whenever you count neutrons, you should get thermal neutron spectrum. And this is what I demonstrate here. And to succeed at neutron counting, I realized there are no tools on the market that allow doing this easily and conveniently. So I had to develop my own hardware and software. So as a one of the outcomes of this effort, I developed this automated nuclear lab system, which you see pictured here, which is a tool for rapid nuclear experimentation. So this system is coupled with software, and it allows capturing data from individual radiation detectors, be that neutron counters or gamma counters or combination of neutron and gamma, or you can connect any nuclear detector to it. And you can acquire data on each channel individually, and you can process this data using the Pulse Counter Pro software, that I also developed to support this system. So this combination of automated nuclear lab and Pulse Counter Pro is an essential tool for me, and I'm proud to say that many other researchers, including a group at MIT, is using it now for their own research, because it's very convenient to capture data, to analyze it, to see spectrum, to eliminate noise, to do all sorts of number crunching and statistical analysis that you must do when you perform a nuclear experiment. So it's a scientific grade hardware and software system that makes this experimentation possible. And key motivation for me was somewhat amateurish approach by a lot of experimentalists to nuclear science, because few realize that taking a single measurement means nothing. And it's the basic principle of nuclear science is nuclear science obeys the laws of quantum mechanics, and in quantum mechanics everything is a random process. So any measurement you take, be that a neutron count, gamma count, X-ray count, any kind of measurement you make gives you a random number. That's just the nature of the thing. So you take one measurement, it means nothing, because it's just a random number. So suppose, I used my neutron detector, I took a measurement, and it tell me the counting rate is 17 counts per minute. Well, I cannot make any conclusion from it unless I take a background measurement. So I take a background measurement, and it's 30 counts per minute. Well, still, I cannot say that my experiment is greater than my background, because both numbers are random, and in order to compare them, I need to acquire a bunch of samples that corresponds to my background and a bunch of samples that corresponds to my measurement, to my experiment. So here, the background samples are depicted in red, and experimental samples are depicted in blue. And because these are random processes, the more samples you capture, the better this histogram will fit the Poisson distribution. And that's one of those things we look for in nuclear science, because all of these processes are normally distributed. Whenever you quantize them, you get a Poisson distribution. And once you acquired enough samples, you have two Poisson distributions, and you see the overlap quite closely. So the difference between them is not as large as two random samples might lead you to believe. And when you run a statistical analysis, for example, you're doing a student's t-test, and that student t-test tells you what is the probability that both samples, red and blue, are coming from the same distribution. And in this case, probability of that is 74.8%, which means that two distributions, they only appear different, but in fact, they're more likely to be one and the same. So therefore, this is not a statistically significant result. And a lot of researchers overlook the importance of statistical analysis, and therefore, they report their data and mislead us in believing that something's happening. But luckily, all of this is done automatically in the Pulse Counter Pro software, and this is what enables me to run a bunch of experiments and have an instant conclusion of whether or not I have excess of neutrons, excess of gamma quantas, excess of anything. And this is how a typical experiment run would be. So out here, red is the background and blue is the experiment. So I'm running my reactor, and my neutron counter is counting, and my software is logging, and I'm getting these red bars, which is my background. Then I turn on my reactor, I start getting blue bars. And the plot here is the p-value plot. So the rule here is the longer your reactor operates, assuming your reactor produces excess neutrons, which looks like it does here, right? But the longer it does so, the lower your p-value becomes. So your p-value must approach 0, assuming that your background is different from your experiment. And the longer you do it, the closer the value will get to 0. So that's why I plot this p-trend. So in this case, this particular experiment indicates, in fact, and it says here, p-value is less than 1/10 of 1,000. So it's 0.000, because I run a bunch of experiments, And every time I turn on the reactor, the flux is slightly greater than the background. But the more times I do it, the greater the statistical significance of this result. And this is how I can show that that the flux of neutrons from the reactor is about, I think, 20% or 30% greater than the background. Now, this is how statistical analysis is done for publication quality results. So with this in mind, this picture tells you how the acoustic signal looks in my reactor. So when I turn on that acoustic driver that's mounted at the bottom flange, I start getting this 20 kilohertz sine wave. And that sine wave is not particularly strong. Amplitude here is in millivolts, but if you convert it to PSI, maybe you get 200, 300 PSI. So it's, it's good pressure, but it's nothing spectacular. What is more interesting is these spikes. So these spikes correspond to pressures on the order of thousands of PSI, or sometimes on the order of tens of thousands of PSI. Sometimes they're so great that they destroy my ultrasonic transducer that I use to listen to these sound waves, and sometimes they break the glass in my reactor. So why do these waves happen? Well, this is something that I discovered that if I introduce water droplets, specifically heavy water droplets, into my reactor, those droplets convert into water vapor bubbles, and those bubbles somehow synchronize their expansion and collapsing action. And I hypothesize that these spikes are caused by constructive interference of shock waves that these expanding and collapsing bubbles launch. Specifically, I think that the shock waves constructively interfere when the bubble rebounds, because that's when it launches the outwardly expanding shock wave. And I think this is an important component for my bubble fusion process. So how do I know that I get fusion going or not? So one day, almost like 3 years ago now, I turn on my reactor, and all of a sudden I'm getting neutron flux in the excess of 1,500 counts per minute, 6,500 counts per minute. So on this plot below, below, background is so small, I cannot even see it. So background was on the order of 30 counts per minute. And here I have 500, 1,500. So, there were so many counts, I thought, well, maybe I got a problem. So let me look at the neutron detector signal. So I look at the raw neutron detector signal that I captured. And it's replete with the spikes. And each spike here is a neutron signal. So if I expand this plot, so I expand, the horizontal scale, I do in fact see individual, neutron spikes, which appear as vertical lines here. And I see something else here. This, bunched up, undulations that you see regularly spaced correspond to noise that crept into my data acquisition system through capacitive coupling of my acoustic driver to my my data acquisition system. So on one hand, this is noise. You don't want this noise. On the other hand, this noise is very fortuitous because it shows to me that I get my neutrons, which are these vertical spikes, that mostly, by far and large, coincide with the time when my acoustic driver is on. So I see I get the spikes when there is a bunch of undulations here from the basically from the energized acoustic driver. And when the driver is off, I don't see any neutrons. So this tells me that neutrons happen when acoustic waves bombard my oil. So this, bolsters the idea that bubble fusion takes place. So when I turn on the sound, bubbles expand and collapse. When they collapse, they generate neutrons, and this is, what I'm seeing here. So here is, another example of an experiment run over 24 hours. So for about 20 hours, I was collecting background, and you see my background here is in blue. And my background is rather small. Here it's in counts per second, so it's less than 1 neutron per minute. When I turn on the reactor, I start getting these red bars, and you see they're in excess of background massively. So I turn off the reactor, it returns to background. I turn on the reactor, and counts go on and keep growing massively. And in fact, if the reactor is operating, you would expect your counts, or your neutron counts, to increase with time because tritium is produced. So you start with deuterium, and deuterium fusion results in helium-3 and tritium in equal proportion. But deuterium-tritium reaction is much more likely. So assuming that, bubble persists through this, expansion and collapse process, next time it expanded and collapsed, it has some tritium in it, and tritium is much more likely to react with deuterium. So therefore, one would expect more counts, and this is, what I seem to see. And here is, by the way, a zoom on one of these, neutron events, which is actually a multiple neutron event. So each peak here corresponds to an individual neutron. So, this particular bubble, this particular occurrence, resulted in 1, 2, 3, 4 closely spaced neutron events that, I cannot even resolve, with my software, too well. So they are counted as one. And it tells me that, the actual count rate, was a lot higher because a bunch of these neutrons were, synchronous in time, and therefore, cannot be resolved unless, you deploy more detectors. But in order for me to establish, to produce a publication quality result, I had to show that at the end of the day, my neutron spectrum builds into a thermal neutron spectrum. So it took me about 6 months to eliminate all sources of noise and address all potential sources of systematic errors, and to make my reactor work for several hours nonstop, to where I could capture thermal neutron spectrum. And this is, what I've done, and this is what you see here. And at this stage, I was satisfied that I knew that, what I'm counting is not noise, not electromagnetic interference. What I'm counting is neutrons, because the spectrum looks perfectly thermal, and the reactor was operational for over than 1 hour, and the count rate was 100 times in excess of background. So statistics was solid, neutron spectrum looked good. Systematic errors were taken care of, and that's what I was able to put in a paper and submit for publication in Nature Scientific Reports, and the paper was published in May, and that was the result that I was able to publish. There was another result that I did not publish because it did not fit my own understanding of the process, and this is the result you see on this page. So once again, red bars are neutrons from the reactor, and blue bars are background. So I start, the signal is neutron counts are at the background. So I start counting as the reactor is turned on, and counts grow predictably. When I turn off the reactor, the counts seem to return to baseline. I turn the reactor on again, counts go, and this time even higher. And when I turn off the reactor, I don't see counts returning to baseline instantly. Instead, they take about 30 or 40 minutes to relax. And that is strange, because the idea is, if this is bubble fusion, if you turn off your reactor, there should be no neutrons, because there is no sound. There is nothing that expands or collapses the bubble. So how come I'm still getting neutrons way above background? So I turn the reactor again, the counts keep going up. I turn it off again, and counts take their time to return to baseline. So as you see, this was happening all the time, and it took it eventually a very long time, like several hours, to return to baseline, completely. So I waited overnight. I started in the morning, counts went up again, and the whole thing repeated. Because this result was so wild, I decided not to include it in my Nature publication, because this smells too much of cold fusion, and I wasn't sure if my paper would be accepted anyhow, so I decided not to make my task even simpler. So if you read my paper, you see that I don't claim fusion. All I claim is observation of neutrons, because according to academic standards, I have not satisfied the requirement of proving that these neutrons are from fusion. And in order to prove it, I would need to detect tritium, and this was a whole other set of measurements that I didn't have a chance to do. So therefore, I couldn't make this claim, and I decided to focus just on reporting the neutron signal. So this doesn't fit the standard paradigm. So I figured I'll sit on it, try to understand it better, and you are among the first people to hear about it. But let's kind of go back to what I know and what I don't know, because what makes scientific work interesting and frustrating at the same time is because there are always more questions than there are answers. And you think you start with one hypothesis, but it takes you somewhere else. And what you think about the process ends up being wrong. And this is kind of the lesson I learned. So I started with trying to prove to myself that I can do conventional thermonuclear fusion within the cores of collapsing bubbles. But this graph shows me that this is not what is happening, because this graph is incompatible with that idea. yet yes, I see this neutron flux. So what do I know? Well, I know that I mixed my perfect working fluid by accident because 3 years since I've reported this neutron signal, I was trying, to mix the same working fluid on purpose, and so far I failed. And this is, where the frustrating part of science and discovery comes. So sometimes you're graced with this unexpected discovery, and you have no idea how you came about it, and then it takes years to understand and comprehend it and do it on purpose. But nevertheless, here's what I've learned. So my main component of my working fluid is mineral oil. And that mineral oil was heavily oxidized from various fruitless experiments. So I would run my reactor for hours, and the oil would get heavily oxidized. So it was yellow and green in color. So it was somewhat green in color because the gaskets in my vacuum system are copper, and oil was in contact with it. So quite possible that I've developed some copper soap that gave oil its green color. And because you see boxes of borax stacked behind me, those were for neutron protection. They were leaking, and maybe some of that borax have gone into oil. I definitely had some deuterium oxide or heavy water in my water because I added it on purpose. And I did have some titanium deuteride solid particles in it by accident. So one of my fruitless experiments was with heavy water and titanium deuteride, and I ended up dumping it into my waste bucket. And from that waste bucket, I drew oil for one of my experiments, and that's when I've gotten my best results. So too bad I didn't record what I was dumping in my waste bucket, but customary, we don't maintain a log of our waste, so I did not. But this is the irony or serendipity of it. I never thought that oil from the waste bucket would do anything, but turns out it did, and now I'm suffering for the lack of a record of what went into that waste bucket. But anyhow, what else was there? Well, there were some deuterium bubbles in it, possibly a small or definitely smaller amount of hexadecane D40, which is fully deuterated mineral oil. Some amount of xenon. What I also know is that my particles, be that bubbles or droplets, carried significant electrostatic charge, because as I was pumping my oil through the circulation loop, the oil was getting charged because when you use a filter has some paper in it. When oil passes through paper, we have dielectric flow goes through dielectric. When you rub two dielectric together, static charge builds up. And that static charge build up, I could see it, I could feel it, and it was my hands. If I move my hand towards the oil, the hairs on my hand would stand. And if I took my electrostatic meter to it, the meter would go to the chart. So oil was supremely charged sometimes, and I could also see the level of the oil through my viewport. It was not flat; it was curved as a crescent of the moon because there was so much charge in it. And I also had this secondary circulation pump connected to the reactor through Teflon tubing. And Teflon is a dielectric, and it was creating another source of charge for that oil. And when you have electrostatic charge, that makes suspended particles, droplets, bubbles more stable against coalescence, against dissolution, and also changes the bubble dynamics perceptibly. So perhaps that was important also. What I also learned is I was able to produce my neutrons when my emulsion was at various concentrations. So it could have been so thick to where it looked yellow because there were so many droplets in it, and it would still produce neutrons. Or sometimes it looked almost clear, and the only way I could see particles in it is when I would shine a laser beam. And then when you have suspended particles, the droplets in your oil, the laser beam would illuminate them, and you would see the beam going through the oil. But if the oil is completely free of particles, it would be clear and beam would be invisible. So I know I was able to do it at various concentrations, and I was able to do it at various pressures also, from a low-grade vacuum of a few torr to down to atmospheric pressure. But most of my experiments I conducted on the partial vacuum of about 4 to 20 torr, and oil was mostly clear, so it had very few particles, because in this particular mode, it was easy for me to get repeatable results. And as I said, I ran my reactor for about 6 months. day after day, collecting this data and studying, making experiments. So this process was very repeatable, and oil was very stable. And the most often, I would evacuate my oil to about 4 torr, introduce just 1 milliliter from the waste bucket of that magic mixture that I was researching, and I would capture a strong neutron signal until the pressure in the reactor would build up to 20 torr, and then the process would stop. So I thought this was the case because at about 20 torr, water vapor would condense back into a liquid at atmospheric at the room temperature. So that's pretty close to the heavy water vapor pressure at atmospheric temperature. At the room temperature. So this is what I know. So the results were repeatable and sustainable for months and hours, but unfortunately, after about 6 months, my emulsion separated, and it no longer looked the same. So it looked cloudy, but one day in March, I look at my emulsion and it looks transparent with some sediment on the bottom, and that's when it quit working, and that's when I started my work in earnest trying to recreate this emulsion. And I also, always used a 20 kilohertz driver when I was getting, successful results. And the driver was with a duty cycle of 200ths of a second. So the sound was on for 200ths of a second, and then it was off for 200ths of a second, and so on and so forth. So what I don't know. So I don't know, as I said, that the neutrons came from fusion. And I mentioned that in order to establish with scientific accuracy that the neutrons come from fusion, you either must capture neutron spectrum, and not thermal neutron spectrum, but actual neutron spectrum, meaning the neutrons must not thermalize and must hit your detector right there and then, so you could capture their true energy. And then if you observe neutrons at energies consistent with DD reaction, then you can say, yes, these neutrons are consistent with DD fusion, therefore, it's DD fusion. Well, if this is not possible, and then it's definitely difficult in my case, because when neutrons originate from oil, they are going to come through oil, and they're going to thermalize in the process, and as such lose their original energy, thus producing a thermal neutron spectrum, which is a nice spectrum to have, but it doesn't tell you what was the original energy of neutrons. So therefore, you cannot use spectrum of neutrons to determine whether it was DD fusion or some other type of fusion. So in this case, you must look for tritium. And if you determine that your reactor is producing tritium, it's significantly above background levels. And once again, you can say, yes, my neutrons are from DD fusion because I do get tritium, and the amount of tritium is consistent with the amount of neutrons that I'm counting. And that was my intent, but I never got around to doing it because it took me 6 months to prove that I am counting neutrons and to build this beautiful thermal neutron spectrum that you saw. And I meant to start measuring tritium levels, but that was the time when my reactor quit working, and I never got around to doing it. And this is just emphasizes the difficulty of doing, scientific work, especially nuclear work. Every measurement is a difficult one, and every measurement, takes time and expertise and knowledge to do. And measuring tritium is not easy. Perhaps it would have taken me another, 3 or 4 times just to learn how to measure tritium levels. But as I said, I've never gotten around to do it. Yeah, but I will, as soon as I'm able to recreate this magic, mixture one more time. So I do not know whether this was fusion, but it could have been spallation. So if you ask what other process could produce neutrons, could be spallation. So spallation is a very well known nuclear process when you rip off neutrons from other elements, such as carbon, oxygen, or even metals. So for example, when an ion beam hits a metal, maybe when a proton beam hits mercury, it would rip off neutrons in massive quantities, and that's a very well-known source of spallation. But it's also possible to have gamma quantas rip off neutrons from oxygen or nitrogen and produce neutrons in that way. It's also spallation. So I also don't know whether my reaction took place in the surface or in the bulk. So on one hand, my entire reactor is filled with these bubbles. On the other hand, bubbles collapse both on the surface and in the bulk. So I don't know which bubbles did the work. Perhaps both, or perhaps one kind. But it's a question that needs an answer. So I don't know the exact composition of my working fluid. I listed all the components in it, but I don't know the exact proportions. I never gotten around to measuring it, because I was so focused on darn neutrons. I also don't know the bubble size distribution. So the tool I used that led the red laser diffraction system in the background, it wasn't particularly good for measuring, the kind of bubbles I had. But that's, again, it's a problem in its own right. How do you measure these bubbles and droplets, and that your measurements are correct? There are a bunch of tools you can find for measuring oil droplets in water, but when the problem is in reverse, when you have water droplets in oil, those tools occasionally yield weird, incorrect results. So it's a problem in its own right. So someone needs to spend time on how to measure water droplet size distribution in oil, and once again, I wasn't able to devote enough time to it to obtain certifiable measurements. So I don't know why my neutron signal was increasing with time, but I have an idea. If it was fusion, it would breed tritium, and therefore probability of subsequent fusion reaction increases, because now we're talking about deuterium and tritium reacting. So this is not an exactly accurate statement. I could say I do not know for sure why my neutron signal was increasing with time, but I have a pretty good idea, and it's consistent with fusion. But for the life of me, I don't know why the neutron signal remained when I turned off my acoustic driver. So that's the biggest mystery, and that didn't happen all the time. It happened enough of the time to where I can rule it out as something weird. Most of the time, the neutron signal disappeared instantly when I turned off the acoustic driver, but enough times it didn't do so instantly. So therefore, something else was happening, and that begs an entirely different question, and that question I'm going to address shortly. But before, I want to kind of summarize what I tried. So I spent 2.5 years trying to replicate this mixture, and without success. So I tried to work in just with heavy oil, and what I've learned is with heavy water in oil, does not produce neutrons. So clearly something else must be tried. So I thought, well, maybe if it's not heavy water, maybe it's this titanium deuteride powder that I had. So I spent another year on this titanium deuteride powder without much success. So I also tried pure deuterium bubbles and deuterium and xenon. That didn't work. Tried surfactants, didn't work. So tried a bunch of things, listed here: charging oil, developing stupendous acoustic pressures in excess of 50,000 psi to where my reactor was bursting at the seams and the welds were coming apart. None of that, seemed to produce any results. So the conclusion that I arrived, it's not a single one of these things. It's a combination of all of these things. And it makes it more difficult, because it's easy to, let's say, take oil and heavy water. So you have two things to work on. You can scan the parametric space. But if you have many of these things, the parameters grow in combinatorial explosion. So it's just too many things to try. So how do I approach it? It's kind of a question. So one thing I've done, I've applied for NSF grant. There is a seed fund grant that I was invited to apply, and I did apply. So it hasn't been, decision hasn't been made yet. I don't know if it hasn't been reviewed. But what I know for sure that for me to make progress, I need to basically I need to outsource some of the tasks. And one task is CFD modeling. Another task is high-speed diagnostics of bubble behavior. Third and rather important task is to make a system that mixes bubbles and droplets of specific size. And that's why I applied for a grant, so I could have some money to spend on this task by hiring people who are able to solve this well-defined problems and produce subsystems that I badly need to make progress in a bit more systematic manner. But that's the nature of science. If it was easy, everybody would do it. And I feel like I've done the easy part. Now it's the hard part, and that hard part, unfortunately, requires money to buy top talent that is necessary to address some of the issues that I highlighted. But what I'm thinking now, I'm thinking that TID is titanium deuteride was probably crucial because I cannot think of any other way to explain why my neutron emission did not return to baseline right away when I killed the sound. Because if you hypothesize that fusion happens within the solid state, within this titanium deuteride particles, then it's no longer a conventional thermonuclear fusion. It's some sort of cold fusion that we don't know anything about. So who is to say that that process must stop when you turn off the sound? So that's the only explanation that I can think of right now. And I also think that the static charge might be important because static electricity on the surface of these TID particles could do something. Also, it could prevent these particles from coalescing. And I think the mechanism, the onset mechanism of fusion is this cavitational jets from droplets, from water droplets or bubbles that I have floating in the soil alongside of my TID particles. They impinge on solid TID particle surfaces and they initiate the fusion. So I'm thinking that I should go back and try generating these nanobubbles again and add some TID particles to my mixture and see if I can get any headway that way. So the working theory, once again, I think my mixture must contain these three components. So it's, first of all, it's oil, but within that oil I have this D2O droplets, and these D2O droplets turn into D2O water vapor bubbles, and those bubbles expand and collapse violently and create these cavitation jets that impinge on solid titanium deuteride particles, and the fusion happens in solid state. So if that is the case, well, I'm thinking about making a bottom flange of my reactor from titanium and deuterate the surface of it, to maximize the surface area, and then introduce the fluid and see if the cavitation jets impinging on deuterated titanium bottom plate of my reactor would produce massive amounts of fusion. So that's on my to-do list. But I also tried synthesizing my own titanium deuteride powder. So before I was using titanium deuteride that Alan Smith made for me, and that powder was rather coarse and it was electrochemically loaded. So I thought maybe I can do some of that powder. I thought I have a picture here. Somehow I don't. Well, I thought I would make that powder myself. So I took a cylinder, which you cannot see. It's behind this neutron detector. And that's, the picture here, which is missing. I apologize for that. So this cylinder, which you cannot see, is filled with titanium sponge. And then from the cylinder, deuterium gas is fed into that titanium sponge. And then the cylinder is heated. And when the cylinder is heated, the titanium sponge is heated. It absorbs deuterium. And as I was doing it, I was capturing neutron counts. I thought, what if, I get some anomalous neutron counts just from the deuterium loading into a titanium sponge. So the blue is here is background, and red is, when I actually applied heat and when hydrogen started being absorbed by titanium. But these counts are consistent with background. So you see the red bars are now taller than the blue bars, so the count rate wasn't changed. So the p-value approaches unity, which means natural neutron background is the same as the neutron background when deuterium is absorbed by titanium. It was just a curious experiment to try. But at the end of the day, I developed enough of this powder, about 1 pound, that I put on eBay for other, researchers to try and experiment with. And that's the powder I intend to use in my subsequent set of experiments. Which also, give me some other ideas. What if maybe, surfactant is more important, or maybe, static electricity is more important, which reminded me of another work by a Russian group that happened about 20 years ago in Russia. So what you see here is a reactor very similar to mine, and it's also filled with mineral oil. And that oil is passed through that reactor through a Venturi nozzle. So that's an elongated Venturi nozzle that you see in the middle. And it's passed under very high pressure. And as oil exits the nozzle, it glows. So they don't really know why it glowed. And I think this result in its own right is just unbelievably interesting, So you pass oil through a Venturi nozzle at such a velocity that the oil glows. So I think this glow is electrostatic in nature, because oil is electrostatic and it rubs against the bulk of oil that is static. So the oil jet impinges on the bulk oil, and charge separates, and the charge creates so much friction, and you have a bunch of this electrostatic discharges jumping on and off, and this is the glow you see. So I thought, well, this is very interesting to try to do this setup and introduce my heavy water droplets or my deuterium bubbles in it. But this is a bit of a scary experiment to do by yourself, because oil is under pressure, and if it bursts, it can ruin my lab or even ruin me. So I'm interested in doing this experiment, but I'm wary of doing it by myself, because there will be nobody to hold my body away from from the sparkling wires or from the cutting jet of oil that bursts through the line. So I'm kind of being a chicken at this moment, trying it by myself. But maybe if I get funding from the grant or find a collaborator, I could try a version of this experiment, and we could see if we get neutrons this way. So the guys who did this work in Russia 20 years ago, they didn't use deuterium or deuterated oil. They used just ordinary mineral oil, and therefore they didn't detect any neutrons. But I think it's a very interesting work to build on. Well, my talk is coming to an end. So because my publication in Nature Scientific Report created a lot of interest, I was encouraged by a few folks to put my project on WeFunder. And WeFunder is a crowdfunding platform that allows anybody to participate in this project if they find it interesting. And few people did. So to learn more, you go to wefunder.com/maximus.energy, and you learn everything about it and how you can participate. And that's all I can say. It's under regulation crowdfunding. You don't have to be an accredited investor, but if you can raise a little bit of money, this research can go to the next stage, because I am pretty much at the end of where I can make progress on my own. And clearly, additional involvement of technicians and skilled people are required in order to make progress, because there is enough of there is just too much work for a single person to do. And finally, if you want to read more about what I've done, of course I refer you to my paper, Observation of Neutron Emission During Acoustic Cavitation of Deuterated Titanium Powder, Nature Scientific Reports. It's an open access. You can read it freely online. I also encourage you to visit my paper, Reliable Neutron and Gamma Detection, which is published on my website, maximus.energy. So that paper describes the neutron measurement techniques I reference. If you want to learn more about the hardware that I employ, the hardware that I make, I have a white paper about it called Automated Nuclear Lab, and a paper describing the pulse counter software. So everything I do, I hold nothing back. Everything is disclosed in my publications, how the software works, how pulse processing works, how spectra is reconstructed, how hardware acquires data. So all of that, you can read. So, and some of additional results, are published at Maximus Energy blog under bubble fusion, which you can also review. Well, I think at this stage, I am happy to take any questions.
Okay, awesome, Max. That absolutely amazing. So let me do this. I'm going to take down the slideshow. I'm going to bring the crew back in here. Let me see if I can squeeze everybody into the lab. Okay, I think that's everybody. Please put your hands together. Give an enormous applause to Dr. Max Fomitchev. Max, thank you again. So again, for me, this is so exciting, because LENR in general is something that has been producing results for decades, but it's been very difficult for science to kind of wrap its hands around it. And so what you're doing is it's kind of a different approach to it. And I'm just looking at that going, okay, maybe this is it, right? Maybe this is the breakthrough that we've been waiting for. So.
Yeah, you're very kind, and I certainly hope so. And that's why I hope that more people can join the project, because I need more people in order to make further progress. Because only so much work one person can do before being burned out. And
Yeah, no, and this is what the APEC community is all about, So, what I want to do actually, I very quickly I want to share. Let me see if I can. Yeah, okay. And where is it? I want to share the Maximus Energy website just in case anybody hasn't seen this. It's maximus.energy. I'll drop a link into the chat for that, and so that'll be there. But this is your website. You make nuclear detection equipment,
Right.
neutron
Yeah.
and gamma detection stuff. And then there is also work about your experiments that's on this site. So I want to absolutely recommend that people check it out, check out your work. And if they are working with LE&R or anything along those lines, you also sell equipment. This is something that you
Right,
do.
right. So real quick note, I make my living by manufacturing and repairing and refurbishing scientific equipment, and primarily neutron detectors and gamma detectors and X-ray detectors. But I also deal in all sorts of vacuum equipment and gas analyzers, pressure gauges. You know what. And I'm proud to say that all major universities buy my automated nuclear lab and Pulse Counter Pro software now. So I'm happy to see that more and more researchers use it, and this is one of the ways how you can contribute to the project. And if you need equipment, you use my website or contact me, and I'll be happy to supply you, because that's what funds the bubble fusion work that I do.
Yeah. Yeah. Well, and again, that's why I wanted to kind of showcase your website. So,
I appreciate it.
yeah, folks are watching. Do not be strangers. You've got a lot of information on his website as well as contact info. If you want to learn more about what he's doing, this is the place to go. It's maximus.energy, and there's the contact form right there. So that is the website. I'm going to take that down. Okay. And did you guys have any questions? We've got about 7 minutes, I think, till the top of the hour. Drew, go for it, sir.
Yeah, hi. Awesome presentation, by the way. Have you thought that maybe the titanium titanium by itself is susceptible to hydrogen embrittlement? That maybe somehow you're getting a hydrogen embrittlement of the titanium. You had some contamination that had some titanium in it. And it might just be that you're actually getting hydrogen embrittlement, which is getting it inside the titanium, and it might be using it as a cavitation chamber of some sort.
Yeah, very well could be. It's a good point. Yeah, that's one of the things I need to research closer. Yeah.
Awesome. Drew, thank you. Let me see. Does anybody else have any questions?
I had a point, and I'm not going to claim that I understand any of this stuff, but on a couple of different chat rooms, I saw people mention EVOs in context with this, and Bob Greenier's work more specifically. And I wondered if you were aware of or familiar with the potential that EVOs are doing some of this work.
Yeah, it's a fascinating
the reactions
and a very valid hypothesis. And the way science works, we need to formulate a hypothesis and then go and test it. And that's kind of what my approach was. So the last 2 years, I was testing various hypotheses. My hypothesis was it's just heavy water droplets. So I kind of disproved that. And I thought, well, it's just titanium deuteride. So I disproved it. So now, with your suggestion, I can formulate an experiment. What if it's EVOs? And then, work with heavy oil and this titanium deuteride, and just focus on energizing it with static electricity as much as I can, with the idea of, maybe higher static charge will create these EVOs, or maybe use that nozzle, that glowing nozzle that you saw, which is bound to create some EVOs. So yeah, it's one of those things I need to test, and that's a very valid suggestion as well. So thank you for it.
Awesome. And then let me ask Bernie. Bernie, did you have any questions? I think you mentioned one in chat earlier.
Yeah, I'm just in the midst of working, so I can't really say too much. But if I could get maybe Max's contact later on, and Tim, maybe schedule the three of us together for an interview, I can write up a whole list, because there's a lot of relevant work in my own electrolysis experiments that I see a lot of parallels with what Max is doing and has come forward with.
Yeah, absolutely. I'm not sure about a three-way interview just because my schedule is pretty messed up.
Fair enough. One-on-one with Max would be awesome too.
Yeah, I would say jot down the questions, mail them over, and I'm happy to forward those on and connect you guys.
Appreciate it.
Absolutely. Yeah, again, we are going into just an absolutely crazy holiday season, and so it's all good things though. In fact, during lab time, I'll show you guys some of the stuff that we've been up to lately. But so I think we have about 4 minutes left. Did anybody else have any questions?
Yeah, I had a question. If let's say you got funding or people showed up at your lab willing to work, what would be the next steps? Do you have a vision of the future?
Yes, very high on my priority list is the ability to hire, a technician or collaborator to work with me full time. Because my biggest problem, whenever I run my experiment, I cannot take notes, or if I take notes, I cannot run my experiment. Or sometimes you need two people, to run an experiment because if it goes, because I had oil sprayed all over, my lap.
You only have 2 hands and 10 fingers.
Right. So
a recommendation on that note, why not just have a camera there so you can at least have a historical recording, and you can go back and kind of like piece together the notes from that.
That's an excellent idea. Yeah. But, answering Mark's question, if I get funding, my first order of business would be, to hire a technician to work with me full time, because, the experimental setup needs, building and rebuilding, like on a daily basis, and I can do it in only so many times an hour. But one of the jobs that I want to sub out is to build a system that generates bubbles and droplets of a specified size, and specifically water droplets in oil. And I know there are off-the-shelf systems that can be purchased for it, but they work on low viscosity oil. So for them to work on high viscosity oil, they would need to be adapted. So that's one of those well-defined tasks that can be solved with money, if I had money to spend on buying parts and having someone to work on it and build that system, and then actually work on the goddamn bubble measurement, because I spent a bunch of money buying these various laser diffraction systems, and I learned that they're not easy to work with. You need to really invest time into learning how to measure and how to calibrate, and that's another job that this other person could be doing, because it doesn't help you to generate bubbles unless you can measure them, right? And it doesn't help you to measure, and then not sure if your measurements are correct or not. And one of the problems, there are no calibration standards for water in oil bubbles. There are calibration standards for water-based.
I would just offer this piece of advice. You can probably find people that are willing to invest their time, even if they don't have money, if they have spare time. Just like you're passionate about it, you can share your passion and find people that are local that are interested in, in working on something like this. And then, if it ever actually gets anywhere.
An excellent advice. And I sort of followed on it, but unfortunately the people that came forth and offered help, they failed at delivering. So
yeah, that's a big problem. I deal with that too. But right. I have found people, just by reaching out. You're at the APEC conference right now. You tell everyone where you are. Maybe that would be more helpful.
I'm in Naples, Florida, right? So if you're in the area or if you're not in the area, it doesn't matter. If you can help me with the bubble/droplet generator, that would be great. If you're in the area and you're looking for a job, I'll be happy to employ you.
That's Naples, Florida.
Yes, Naples, Florida.
Oh man.
So I need to move to Florida.
So, Max, I also wanted to recommend, in my previous job, we were doing powder metallurgy. So we were using a device called, micro track particle size analyzer.
That's what I'm using. That's what I'm using now.
Oh.
Micro track nano something. I forget. Yeah, micro track nano something. It's excellent, but the problem I ran into it works very well with water-based systems. So it should work with oil-based system, but I couldn't get the calibration standard to perform in the oil-based, and that's one of the problems. I asked solution for it. Just make me a standard that's oil-based.
Well, as of a few years ago, they had pretty decent tech support. So hopefully,
I reached out to them. They didn't have a solution. You said you just need to work on it because they sell this in a water-based standards. We tried to convert them to oil-based, and there were problems. So that's where work comes in. And unfortunately, it's grinding grueling work that enthusiasts, weren't interested in doing.
There may be a closed form solution. So they're basically measuring the diffraction of a couple different lasers through this stuff, right? So it's because the refractive indices are different and the dispersions are different. In theory, you could account for what that effect should be analytically on paper.
Well, it's a different problem. The problem was of particles clumping, or it's mostly like particle clumping. So whatever particles they make, they have surfactants for water, but they don't have surfactants for oil. So you need to make particles that are certified under electron microscope and have surfactants for oil, and they don't clump, or you need, to figure something out. Either way, it's job. It's job that somebody needs to do. And as I said, there are only so many hours in a day. I can be making equipment, so I can either make equipment or I can run experiments. When I don't make equipment, I don't have money to run experiments, right? So when I make equipment, I don't have time to run experiments. So it becomes, you have to compromise, and that's why sometimes it takes years to get a simple job done. Besides, if I go off and do something else, it's hard to come back and remember where I was. And then,
And so, guys, we're 2 minutes past the top of the hour. So, again, I want to, Max, let me thank you so much for your time today. Let me recommend, once again, everybody visit maximus.energy. That is your website. The work that you're doing is absolutely amazing. I have become a tremendous fan, and I have a feeling you're going to have a lot more fans after today.
Thank you. I appreciate it.
So thank you so much. Again, guys, let's put our hands together one more time for Dr. Max Fomitchev-Zamilov. Thank you, sir. And so what I'm going to do now is take everybody back out, and we are going to go to Eric Reiter. And Eric, you have, let me see, part 2 of a serious challenge to quantum mechanics. So I want to thank you for joining us today. As kind of an aside, Curtis Horn had said to me, he's like, after the last time he presented, he said, thank you for having Eric on. He has a ton of people who love his work out there. You got to have him on again. And so that was why I reached out. So thank you, sir. Oh, and Eric, it looks like I'm not hearing your mic. I did earlier, so it looks like something may have changed. No, let me see. Let me unmute you. Yeah, it looks like you're muted. Okay. Nope. Do you want to go into settings? So there is a settings button down at the bottom of your screen. Okay. At the bottom of that window, there should be a settings button. And then there should be audio, and it should say what your audio is. And you've muted yourself again, so you need to unmute yourself. Okay, so there is this down at the bottom of your window, right in the middle. There's mute, stop cam, and then settings. It's a little gear icon. If you click that, sorry, Eric, you're muted again. Number one, so. Okay, so now you're unmuted. That's good. So go down to that, try and click that settings button. Okay, and then in audio, in the settings, does it show your mic? Okay, and I'm not sure. So when you talk, is it showing green dots for it lighting up at all? You might try selecting your microphone, or you could try selecting a different.
Yeah.
There we go. There we go. We got you. We got you.
A different microphone came in. I tested it earlier, And I
Yeah.
saw that we're now changed. Anyway, look, thank you,
Okay.
Tim.
No. Oh, you're absolutely, absolutely. You know what? This happens. It's yeah, computers. So Eric, let me thank you once again, sir. No stress. And what I'm going to do is I will disappear into the background, but I will still be here, and you can use the back and forward buttons. If you
Can,
hover over the slide, you can
do you
change
see my
those.
mouse?
I don't see it, but you should be able to see it.
I wanted people to see the mouse. What I'm talking about and looking at. I see it. I thought everyone would see it.
No,
Oh
unfortunately.
gosh.
Okay. Well, Eric, let me take myself out, and if you want to get started, I will be here for you.
I almost want to go
Get
to
your laser pointer and use that, the little red thing.
No, a laser pointer won't work. No, I almost want to go to not using what's stored here and use my shared screen.
Well, we are broadcasting live right now,
Any
so
kind of stick to point to what you want, a ruler just to point to it instead of.
All right, I'm just going to start talking.
Well,
okay.
I'll get you a pointer.
See, I try to do everything connected to experiment. This is a strong claim. I'm saying quantization itself fails. So the experiment is this picture. We're going to look at it in detail. And there are the slides. I have many slides and much detail. I implore people to go to the slides and read it to see the details of what I'm saying, because I'm going to go through it quickly. So I found that there are additions to the properties of the wave that can make it all work. There are threshold properties, which could and beat properties and ratio properties. I'll show how those are identified in people's past experiments. And then we're going to use those properties to our famous constants and equations. And I call this the threshold model. So going back to Planck's work, people think Planck quantized light. It's not true. There are different derivations of his black body equation, maybe hundreds, and I did one as well. But in the famous 1900 work, and Planck also clarified this later in his book, that he was quantizing the energy in material oscillators, not energy itself, the way everybody talks about it. And of course, then Einstein did quantize energy itself for the photoelectric effect. And most everybody argued against it, including Lorentz, saying, well, light quanta just won't do, for good reasons, the wave properties. So in the Bohr-Einstein debates, the Bohr's book clarified just what the model of the photon was. And it's about that there's no visualizable way to see it. There's a reason why people say nobody understands quantum mechanics. It's because it's about giving up understanding, and you could see how it reads right here. There's one sentence that explains it all. If a semi-reflecting mirror is placed in the way of a photon, an h nu of light, whatever it is, leaving two possibilities for its direction of propagation, the photon may either be recorded on one and only one photographic plate situated at great distances in the two directions in question, or else, and this is part 2 of the photon model, or else, coming up, this is part two, we may, by replacing the plates by mirrors, observe effects exhibiting an interference between the two reflected wave trains. So it's two parts that are in contradiction to each other. And so I'm saying take the photon word as a model, not a thing. So here's my picture of the experimental enactment of that model. And all the other experimenters understand this is the way it works. The one way or the other idea, it comes from energy quantization. If you think energy is quantized, you start with one quanta, it should end up with one, but not both. The other half of the model, you reconverge the beam, you get a wave property. I'm going to show that it's this first half of the model that fails. I show how it fails. There's all this wave particle confusion. Please don't look at the double slit experiment. It doesn't have nearly enough to explain what's going on. It's just a statement of the paradox. And people talk about quanta and photons to begin with, and they're all confused. Like here, you cannot really distinguish the resolution of what's going on with quantum mechanics by hacking away at a double slit experiment, which is just going to show you diffraction, whether you do one slit or another or whatever. This is the way to do it with a beam split coincidence experiment. And then, so great people, here's Heisenberg talking, saying, well, if it goes one way or the other like this at a beam splitter, it implies entanglement. It implies faster than the speed of light, everything connected to each other. And all of these acts of desperation. And our friend Raymond Chow wrote a paper about this very passage in Heisenberg's book. I build upon Planck's second theory, where there's a continuous absorption and an explosive emission. This is Planck's drawing, and I add in other colors. Everything in the black and black boxes is by other people, and the other colors is my markups. So in this Planck's second theory, his action constant is a threshold, not a quantization, and it's also a property of matter, not light. It's important to understand that different derivations with different models can come up with the same equation. So physics is about sorting all this out, looking at the different equations and models to make it consistent over them. And that's what it looks like I've done. Well, you'll see from the examples. Also, Sommerfeld worked on this loading theory. It was called a loading theory originally, and our textbooks call it a accumulation hypothesis. And the Millikan was disturbed about the photon model of the photoelectric effect. And in his book, he argues both ways, but he came up with a reasonable alternative to the photon model, which was that it would need only a minute addition of energy to emit an electron. But he didn't see how it can work. And after this writing, nobody explored this idea. It was just gone to obscurity. So in review, there was Planck's first theory, quantized absorption, quantized emission, then continuous absorption, quantized emission, and then there's this preloaded state that would only need a small amount to set it off to show what looks like a quantized emission, to give it the illusion that everything is quantized. But you don't see this absorption thing. But people tested that by measuring how long a time did it take to load up. But they compared to Planck's second theory instead of this Millikan's adjustment to it. And they argue in important books and all of our textbooks that the loading theory is impossible to make work. This is what happened to the loading theory. I'm saying they compared an unworkable alternative to quantum mechanics. And they said, well, that's it. And so soon the Compton effect showed up both experimentally and theoretically to have a particle energy and momentum conservation model. And when people saw that, they were thinking of energy conservation in terms of quantization. And you can see it in many writings. I gave an example here that they think that way. It's just not true. You can have energy conservation without quantization, but they were thinking about all the experiments that way. And similarly with the Compton effect, the coincidences between the two directions of the X-ray signature and the electron signature, that they happen in coincidence, but they were not thinking about, well, how would that eliminate an alternative? They again were comparing to the unworkable loading theory that was about continuous absorption, constant continuous absorption of like Planck's second theory. So they again thought quantization was right. So now de Broglie comes up with his wavelength equation, and I'm looking at the derivation of the wavelength equation. Step one, well, we have E equals h nu, that's cool. E equals mc squared, oh yeah, that's great. Let's just cram them together. Well, if you were to take the frequency from this equation and compare it to the frequency that's easily obtained in the wavelength equation, you get something completely different. So these two equations do not support each other. This is just wrong. Well, sure, in pair creation annihilation it works, and in other nuclear reactions it works, but it does not work with electron diffraction and matter wave diffraction. But people saw that there was something right about the wavelength equation because it fit experiments like charge diffraction, like I show here at the bottom of the screen. And then, of course, Esterman and Stern diffracted atoms, and it fit the de Broglie equation, as in the bottom of the screen here. So they thought there was something right about the derivation. But I forgot to say that there was something else about this derivation that's pretty nutty. There's a c squared equation equals a phase velocity times a group velocity. If you have the group velocity, which is the particle velocity, if you have that anything slower than the speed of light, the phase velocity is faster than the speed of light. And the quantum people just love it because it implies all this faster than the speed of light stuff that was discussed earlier, like from Heisenberg's clip that I showed you. It makes people like it for the probability interpretation. But it's wrong. It's just too far-fetched. And I'll show you another way to derive that equation. Schrodinger is famous, of course, for his equation, but there's another beautiful thing that's in that same paper where he talks about the envelopes, the beats of his wave function that is the interaction of light and charge. And so I embrace this, but let's look a little closer. Take the equation of the hydrogen spectrum of Bohr, and usually there's h nu on the left here. Well, take the h and put it on the other side, and then you have the frequency of the beats is equal to the difference frequency of the inner waves. And so that's the model that I'm embracing. So that's the beat process that I said we're going to justify. And so far I had the threshold idea and the beat process idea. Okay. And so these are attributes of the matter wave that I'm finding in other people's experiments. Schrodinger hated quantum mechanics straight away. Now we're going to go back. There was that h cubed that would happen in the hydrogen spectrum equation. It turns out you could use that in a derivation of the black body spectrum, and Bose did it. He's famous for using an h cubed construct. So I took that And instead of using standing waves of light the way he did, I'm using standing waves of charge, of Schrodinger's psi. And I was able to come up with the black body spectrum. And it's way too hard to show here, but I'm saying you could click on my other papers to see these theories. Now, here's about antimatter that comes out of this beat model. There's an inner wave, and it's easy to guess that the inner wave would have an opposite phase in antimatter from matter. And then when they meet, the inner waves cancel out. The outer wave is how light interacts. That's light. And then you're left with the light. So I'm getting at the inner guts of the way matter works. What is the matter wave? Without wave-particle duality. See, that's always been the hang-up, wave-particle duality. What's with that? And we have all these acts of desperation as to what's going on. We're cleaning all that up. So I think the alternative propulsion people would like this, because I have leads onto how to understand antimatter. This is one of them. Then there's spin. I have models of counter-rotating beats that lets you have a pictorial idea of spin, and I have equations of it that you could see in my other papers, and models of the atom that you could see on your own. And I have links all throughout this PDF to find these things. But now I'm going to go to the derivation of that wavelength equation without wave-particle duality. We're going to start with the equation of the photoelectric effect and understand that the velocity is the velocity of groups. And then we're going to use this beat idea, but we're going to realize that light interacts, one wavelength fits 2 beats. So there's this factor of 2 correction that I'm making to that idea that Schrodinger had. And it's justified here in my small print. Otherwise, you'd have to square it to make it all fit. But the linearity of the photoelectric effect is justifying just doing it this way. 2 beats per wavelength. So you get this factor of 2 correction. And then you just cram it together with what we started with the photoelectric. And out comes the what looks like the de Broglie equation. So we're connecting a frequency equation to a wavelength equation. And this isn't really the de Broglie equation anymore. It's going to be a non-dualistic wavelength equation. But it has this m, the mass of the electron, that looks like a particle. And so what do you do with that? Because here's a wave, and you got wave-particle duality in the same equation. And that's always been the problem with quantum mechanics. There's wave terms and particle terms in the same equation. Here's how to fix it. We're going to use Planck's idea. And I thought of it earlier, and I went back into history to see who else did it. But he did it where the constant is about a maximum. You don't see sub H action, but we're going to take it as a maximum. We're going to do the same thing with the mass constant and the charge constant. So the message of the experiment when you do electron diffraction is the ratio of the charge to mass in this, the action to mass in this case is conserved. So that's the trick. That's how to resolve the wave-particle paradox. It's that the constants are thresholds and the ratios are what's quantized. So we're going to look at the experiments that are famous for wave-particle duality and recognize that they have these ratios in all of them. There's a beautiful symmetry amongst the equations. So I already talked about the wavelength equation. Oh, let's go down here to the Aharonov-Bohm electron diffraction thing. It has the charge to action ratio. That is a conserved constant as a result of the measurables in the experiment. I'm saying, what is the experiment saying? What is it delivering you? It's delivering you the ratios of these constants, but it's just a ratio. It's just delivering that number, which is the ratio. So what that means, this is what's really beautiful about it, is that, let's take here in my upper right-hand corner, let's say we have charge being emitted, and we're going to see, well, is it a particle or not? So if you take some cubic volume of that charge wave that is expanding out in space, the charge to mass ratio is conserved, and the other ratio is charge to action, action to mass. The ratios are conserved in any cubic volume of that charge wave. The identity of its wave gets transmitted. There's details to the wave. You do not need to have a particle going across space for the absorber to pick it up as a charge event. And so now we can look back to experiments where they saw, oh, well, this is really great. We get the charge to mass ratio in this experiment, and we get the charge in the other experiment. Here's the thing. The charge constant was deciphered in bulk matter. The charge ratios are what's deciphered in free space. So the charge constant, when you do these experiments, you don't see the ratios. It's the thresholds that are expressed by all the other nuclear forces that make an ensemble effect to make it look like charge is quantized. It's really thresholded because it could be anything when it goes across space. It can smear out to be unquantized, but the ratios remain quantized. See, it's an advanced concept. You're going to have to go back to this list of experiments to understand what's going on. So that's what I say is going on. So what goes across space can transmit its identity to the absorber, or let's say charge, or an atomic wave, a wave function. And I'm going to show you that experimentally. I did an important experiment to show this. So far we have looked at past experiments, and I'm saying that it has this threshold ratio model to understand wave without wave particle duality, with a reasonable model that you can visualize. It calls for evidence of subquantized charge, subquantized energy, and subquantized mass. It'd be nice to have all of them. I'm going to show you what I did do, which was a lot. To test if energy is quantized, many will invoke this test that I showed before, the particle part of the photon model, and compare to chance. That's how it's done. And we're going to see, well, who did these experiments? Everybody else did it with visible light and one person with X-rays. I'm the only one who did this experiment with gamma rays, and I also did it with alpha rays. Nobody else did anything like that. And this bottom test is a control test to see that we do one at a time. I'll explain that. It's like filling cups. I want everybody to understand what I'm talking about. That it's like a rule. You only see when it reaches the top, and it all spills over at once. Well, usually it'll spill over to one and fill the other, and then that'll spill over. Usually it's 1 to 1. But it can be like this, where there's 2 half partially full, and one could spill over, fill the rest, and then make 2 show up. I'm saying we can find a 2-for-1 effect that pits you against energy quantization but it's not quantized, it's thresholded in order to get a 2-for-1 effect. That's what the experiment is. No other attempt at doing this experiment understood how to use energy budget in their experiment to see, well, how big are the clicks? The pulse height of the clicks are proportional to the h nu energy for the light test. This is the graph of pulse heights for monochromatic light in a photomultiplier. And the people who do these experiments, they don't talk about where they set their thresholds or how big a pulse they use. It's all photons to them. But with gamma rays, you have energy resolution. Pulse height resolution is proportional to the frequency of the electromagnetic frequency. And in this case, I do it with gamma rays. And it's proportional to the energy of detection. E equals h nu is still correct, but it's about the energy that gets detected in a threshold, and it's also about the energy that's emitted at the source. We don't see that directly, but that's the model, that there are discontinuities, but there's also a sub-quantum realm that makes it all work with the wave properties that cause all this entanglement weirdness that everyone is bent out of shape about. So this was the first test done, and it's a beam split. That's great. They're using the chance equation at the bottom here in the well, you could see it in what I excerpted from them. It's the rate in the first detector times the rate in the second detector, singles rates, times a time window. Multiply that together, you get the chance rate, accidental rate that should show up. And you compare the experimental rate of coincidences within that time window, the experimental rate that shows up within the same time window as underneath here. And you see, well, do you get better than chance? They get 1. And then it looks like quantum mechanics, and everybody is sort of happy. And I'm saying, well, I'm pointing out that you could do a histogram of the time between pulses, which makes it very easy to understand what's going on. The time between the two detector pulses is with 0 time in the middle, and if it goes click, click, it'll go to the left, it goes click, clack, it goes to the right. It usually makes this band of noise that says that it acted like a photon, but it's just noise. So then these people do it, and they show that time difference histogram, and it is like people say, or it looks like a band of noise, and it looks like quantization because that's what quantum mechanics would predict. The peak here is a control test where they're putting in something that will make coincident pulses. They're using the same chance equation, and they're admitting if you get any peak in this histogram, you have to rewrite quantum mechanics. Same thing with Clauser's work. Here is the delta T histogram I circled, and it's a band of noise. They don't see through the illusion. They don't know how. They don't understand how to set up the experiment. They're not looking at any kind of energy resolution, where they're little or big pulse heights or what. And there are other problems that they do, where they use polarized beam splitters, and so there's a list of problems. Then they did it again. Now these people had a pair of their H nus come out, one to the left and one to the right, and they used the one going to the left as a trigger, and that goes to what goes at the right to the pair, and it's a triple coincidence test. Now the triple coincidence technique is well worked out by the nuclear physicists, but they do not use the triple coincidence chance equation. So I call them out. They're doing it all wrong. They're making up another equation for it. And what's good about this test is that they do understand that there's a particle part and a wave part to the photon model. But they labeled it wrong, like they what did they say here? Single photon input to the Mach-Zehnder. No, it's not a single photon input because the triple coincidence happens further back. So there's all these little tricky things that people do when they write about this. I corrected this, put the wire in, and this isn't the only case. The literature is full of this kind of stuff. This is a more modern enactment of that same kind of triple coincidence test of the photon model, where they use parametric down conversion, and they're going to try to say it's a triple coincidence by this weirdo comparison to chance. The numerator up here is a triple coincidence rate by experiment. The rest of it is about chance. I don't understand how they got that. I tried. It looks like it's just wrong. But it's much worse than that. They go and throw this equation away and make up another equation that I wrote down here in the right box and use that because it makes it look like it really is a photon because it's even less than chance. And you can tell what happened by looking at the numbers. And my God, how do they get away with this stuff? Anyway, they're using the wrong chance equation, and the whole mess of these people that are saying it's quantized by this experiment are wrong. Please forgive me for my enthusiasm, but it's long overdue. I do the experiment with gamma rays, and I get around all those problems. Most importantly, is to tell when the emission is one at a time. Well, this is a standard technique amongst nuclear physicists where they take a radioisotope and surround it by a pair of detectors. It's in the lower right corner I'm looking at. And we'll look at that time difference histogram, and they get this band of noise that tells you it is not in coincidence, which means it's only emitting one at a time. The whole periodic table depends on these kinds of tests that the nuclear physicists do to tell whether it's one or two or three or what. Then the technique of Eric is to take the same setup and then use a thin detector in front of a thick detector and measure, does it go to make one at a time or two at a time or what? We're going to look at the time difference histogram here, this great big peak. And we get to measure straight away in the oscilloscope how many are there within this time window. We use that time window of which we're counting, and that's the way everybody else does it. And we put it in the chance equation. We get the chance rate. And then we look at this experimental rate and we put it into that ratio. 6 times chance. Now, I've done this experiment hundreds of times in all different ways, scores of different ways. Of course, you subtract background, and people say things like that. They'll try to shoot me down any number of ways. Yeah, there's a small coincidence that happens from background radiation that's subtracted. So I'm only looking at the big pulses. I'm not looking at half-height pulses. So I'm able to say from the pulse height histograms, the singles histograms that are right happening with the experiment all at the same time, this oscilloscope is able to record the pulse height histograms of both channels, the timing pulses, and the actual analog pulses to see that they're well-behaved pulses and not falling all over each other, and the time difference histogram. So I'm recording all that at once and recording the singles rates. It's great. It's the LaCroix oscilloscope. And I developed this technique of how to use the oscilloscope that way. So, right, full height pulses, where I said it so, well, we're not looking at Compton shifted little pulses here. It's a full and a full. It's a 2-for-1 more often than accidental chance. that shows quantum mechanics fails. That's the end of it. So, but I kept working on it all these different ways. Now, why was this effect not previously noticed? For good reason. First, just in the spectrum, there would be some way to see it, and I'll show you that. But you have to know how to look for it. You have to have a gamma ray that only emits 1 per decay. This is important. This graph is the absorption in the sodium iodide detector that I use. There's a better detector that they like using because it has a better pulse height resolution, but it has a problem because it won't show what I'm showing here. The photoelectric effect needs to dominate over the Compton effect into how the detector responds to make its scintillation flashes. It makes little flashes of light inside. And there are these two processes inside the detector, the photoelectric effect and the Compton effect. The photoelectric effect needs to dominate over the Compton effect. If you're over to the right, it's much harder to see this subquantum effect that I discovered. It is possible to see it, and I'll explain how later. So there are only a few radioisotopes that'll fit here. It has to decay to something that's stable and not emit again. It has to have a reasonable half-life to work with, and it has to be in this part of the spectrum. There's another isotope down on the left, but it's too noisy there. So there's really only this sweet spot to do the experiment that I discovered because I tried it further up here with cesium-137 and it didn't work. And so I kept trying, and I looked at graphs and I figured this out, that it needed to be this way. The other reason why this effect has not been previously noticed is because who would expect that the most particle-like kind of light would show that light is not a particle? So that's what happened. And here's another more elaborate test that nails it down pretty well. I do a triple coincidence test. So I start with sodium-22, which emits antimatter, which will, an anti-electron, and then it finds an electron and annihilates, and it makes a pair of gammas in opposite directions. And in one direction, I hit I had to use different detectors. I made bismuth germanate detectors to have that photoelectric effect dominate for this higher frequency gamma ray, you see. That's what makes it work. You have to know what you're doing to see through the illusion. There's another gamma ray emitted in the same radioactive decay that I use as a trigger. Now, you can see that it defies quantum mechanics just with the pair up above here. And I have this great big peak. But even better, I do the triple coincidence and you count the number in the peak here of the pulse height histogram. You compare that number in the middle here to the chance rate, and I get some terrific number hundreds of times above chance. And so this experiment is good because it eliminates all kinds of other ways to say, well, what if there's weirdons going around or something else? I mentioned what those alternatives might be, where you can click it here and see arguments like, oh, well, maybe I discovered stimulated emission or something else. So people come up with this stuff. No, I did experiments and calculations. You can also see it in this experiment. Now we're going to go back to the Compton effect. It turns out that in Compton's book, this great book, one of the greatest books, X-rays in Theory and Experiment, and also Millikan's book was great. Those are two of the greatest books to read. Compton had a wave derivation of the Compton effect experiment effect. But it was kind of clumsy because they had to make standing waves of the de Broglie wavelength counter-propagating waves. It was kind of artificial, and nobody else worked on it. But this beat idea that we found from Schrodinger fixes the whole thing, and the way I derived the wavelength equation. So we used the non-dualistic wavelength equation to start, and then we used the Bragg diffraction equation and the Doppler shift equation and a trigonometric identity, and the Compton effect equation comes right out. A beautiful parallelism between how to derive a experiment for the equation with two completely different models. So that's a good example. Just because the derivation fits the experiment doesn't mean the derivation is handed down from Mount Sinai. But get this, this model predicts that there's a straight through undeflected ray that they deny in the model of the photon that I have up here on the right that everybody uses. It's not supposed to happen, but it's easy to see in the pulse height spectrum that I have in the lower right here of the gamma ray that I'm using here in a pulse height spectrum. So we're going to examine this in the next slide. There's this anomalous shelf of pulse heights that's in the middle of this screen. That shouldn't happen at all. On the left is the normal photo peak and the Compton shifted peak. The pulses within the detector make flashes. If the flashes of light superimpose in time, it makes a pulse that much bigger, like almost twice as big pulses, which are showing up here in this anomalous shelf of pulse heights, easy to see in the spectrum. So you can easily calculate. I show the calculation here. You have to know the length of time the light lasts, and other people have worked on that, and I use a conservative figure for that. And you calculate the rates right from the spectrum. You put it in to calculate chance, and then you see what's there and compare to chance, and you get 6 times chance, which means it's not a photon. It's not supposed to do this like conventional. And then I do it with another radioisotope, and I see it even better. And I did simulations of all this. So there's plenty of interesting work to do here. This is one of the best parts. You know, I tried to publish this, and I I got rudely rejected so many times. I thought, well, I'll show them. I'll develop useful spectroscopies and file a patent. So I did. I sent the patent office 20 sets of data of ways to use this in spectroscopy. They didn't get past the title of what I was doing. Let me explain. Crystallography. You rotate the crystal, do an experiment, measure the subquantum effect, the ratio above chance. You get some rate. Rotate the crystal 60 degrees. Oh, well, should it change? It should be. It went, what did it do? 44 times more. It lit up by like Bragg reflection against the crystal. Subquantum crystallography I invented. So I kept working on it. Well, what would happen if you put a magnetic field on the beam splitter, and then you get to see stiff bonds, or bonds that are flexible in dielectric or ferromagnetic scatterers. You get to see the character of the bond by putting a magnet on and seeing the subquantum effect and how it changes. This is one of the better ones, the next one, the middle one bottom. I electroplated cadmium 109 to see, well, first I wanted to just get more of it. You're able to just buy liquid vials of the radioisotope in water. It's an incredible thing. They sold it to me, and I electroplated cadmium 109 onto the end of a pair of platinum wires. Well, one of them is where it went to. And then from the wire, I do the unquantum effect, and I compared it to your regular cadmium 109, and I also compared it to crystallizing the cadmium 109, evaporating it in a centrifuge. And I saw, wow, the chemical state of how the radioisotope is prepared affected the degree above chance. And it wasn't about like there's more radioisotope or anything, because that cancels out. This is an important discovery. So I'm saying, let's use this in future experiments. Use it on the sodium-22, and then understand antimatter better, stuff like that. Here we have a feedback for crystallography and nuclear physics that's never been seen before. And so I just went on to other things. I tried, well, what would happen if I cooled the beam splitter, like with liquid nitrogen? It made it twice as good with the ratio above chance. All these experiments. So they're not some special case kind of thing. If it splits into two, if you get 2 for 1, maybe you should get 3 or 4 for 1. Well, it does. So these are triggered pulse height spectrums. And this is cadmium 109. The right detector is a trigger detector. It's a beam split. The left detector, we're going to get 2 or even 3 that show up triggered in coincidence by the right side detector in this sodium iodide test. So the big peak here is the photo peak, but it's in trigger with the other one. So that's 2 for 1. So that's why I wrote 2x. The next is twice high pulses triggered by the other detector. That's 3 for 1. Starting with 1 at a time, we know the radioisotope only emits 1 at a time. Then we get 3 for 1, and we could see how much above chance it is with some numbers. And I didn't put that number in here, but it's in my notes. It's in other published places. And here's a hint of 4 for 1. That's nice. So let's see if it worked with the other detector. The liquid nitrogen cooled high purity germanium detector that everybody loves using, and you do see the subquantum effect. So I think Max was asking for this. The spectrum without coincidences. Here's the single spectrum, no coincidence. There's no ×2 peak here. You put it in coincidence with the other detector. This detector has a hole in the middle of it, and I put the radioisotope in the middle with some lead shielding that aims it over to the right so that it goes through, whatever goes through the first detector goes to the second detector. So the shielding is important, and I checked for things like lead fluorescence, and I tried tungsten collimators and all kinds of stuff. So we're not looking at lead fluorescence. We're looking inside this giant shield that I made. This is the chamber of photon doom. So you cut out, most of the experiments I did were in this shield where the background rate is down. Excuse me. Background rate is down to like 1/30 of otherwise. Anyway, there's this ×3 peak. It's 2 for 1 in the main photo peak because of in coincidence with the other detector. This is in the ×2 energy position, energy of detection, to make a 3 for 1 effect. with the other kind of detector, which is nice. And then I also did some more work with the more than one happening in the detector. And I found an effect of distance where there's a sweet spot. If you move the source closer, does it enhance the unquantum effect? The subquantum effect, I've been calling it the unquantum effect for many years, but I'm trying to be nice to you quantum people. I'm going to call it the subquantum effect, saying there's something that looks quantized, but there's something underneath. The ratio of the big peak here to the chance rate. The chance rate is this band of noise, and I've measured that. So what is the rate here? And I see it equals the chance equation. So the ratio of how much above chance is easy to see straight away by just looking at the graph. And the peaks here are all normalized. And so you push it a little bit closer, it's greater than chance than the previous one. You push it further away, it gets worse. There's a distance resonance. And I actually did this many years ago to make the cesium-137 work when I pulled it away. And it was by this effect, when I pulled the source away from the pair of detectors. There's a cone of classical gamma rays that has a transverse size to it when it meets the absorber molecule. If it's too far away, the cone is too big for the energy to be picked up by the absorber molecule. If it's too close, if the source is too close to the pair of detectors, the cone of energy is too narrow. It goes right through. Then it could be just right. And that's what made this distance effect light up. A good deal of my effects need to be reproduced, but I reproduced this several times. And most of what I've shown you, I've done several times. And the basic effect that I showed you first, I may have done 100 times. Now, comparing to what other people did, they don't show any pulse height information. They don't show any pulse shape or the pulse shapes well behaved. They don't show any of that. I show it. And what does their data look like? They look like noise, and I have this great big peak. I'm way ahead of them for all the tests to see if it's a photon. And then see all the other, like these two particle tests for testing Bell's theorem and stuff, all that stuff is depending on the probability interpretation from these experiments that are more fundamental. They know the photon effect, they cite it from these beam split coincidence experiments. And it's from the model of the photon, which is from Einstein. So if you want to argue about what a photon is, you have to argue with Einstein and Bohr. It goes that far back and it's never changed. So what about rest mass? So really, that was the hard part. Because there are experiments that show that it acts like a wave. So I split the atom like a wave, where there's a beam splitter of gold. It should go one way or the other. Usually it's half height. What are these full height pulses? Calculate against chance, 4 times chance. The helium nuclear wave function can split and load up, transmit its identity as a wave, and make a 2-for-1 effect. Because these are big pulses characteristic of the full kinetic energy of the alpha that's emitted. The alpha that's emitted is 5.5 MeV, and if it was to split in half, it would be, it takes 14 MeV to split in half by other people's experiments, and we don't have that. By 14 MeV of kinetic energy to split. So what's going on is that what it looks like is that the kinetic energy is slowed down, but the ratio of the charge to mass is conserved at the detector. So this is actually the full height pulses in this experiment is my strongest evidence to show that we're seeing subquantized mass and subquantized charge with a 2-for-1 effect of helium. And the numbers are all down here and singles rates and everything. I did this is interesting. I did a background test and it's like there were none. What did I do here? I looked at it. Maybe there's one over 3 days of coincident background. So it's not like it's from outer space or anything. And then there's arguments. Well, people will say, well, what about buckyball diffraction or giant molecule diffraction? I have arguments to say they did those tests wrong. You can look back at this. And then I tried to find how to see fractional charge with like a 2-year effort. I had trouble with alpha rays in a mass spectrometer. I wanted to change the charge state with an electron gun. I was able to see 3 charge states, but not able to get the electron gun to work right. There are all these different ways I did the experiment. And then there's this Bell theorem stuff. Well, Bell's theorem does not include a hidden variable in the detector. It's all about what shows up ahead of time in the particle. So Bell's theorem falls short. And so bottom line is that both Bell's theorem is wrong and quantum mechanics is wrong. That it needs to be corrected. There's more about Bell's theorem if you want to see it. And they really mean it. And it's like, well, they have some nerve. And they're all going down. It may take past when I'm dead, but that's what's going to happen. Now, if you're going to talk about this stuff, it helps quite a bit to not talk about photons going across space because it's dualistic. So please just talk about the clicks in your detectors. Talk about what the experiment says. And this is like an overview of how I try to hint as to how to do it. If you have any doubt as to what I'm doing and saying here, and surely you will, do the experiment. I'm showing you just how to do it. Buy this radioisotope and do the pulse light spectrum. You won't see this anomalous shelf unless you go to logarithmic. And here I show with the helium, the liquid nitrogen cooled detector, the HPGE, that you do not see the anomalous shelf. I think Max was asking me for that. Here it is. Do the experiment and argue with the experiment. And, what's next? We were warned. I stand with Einstein, who argued against all this in 1935. Schrodinger opposed the whole mess of it, the probability interpretation. You can read it here. And right away, Lorentz, from his analysis of a telescope, which was great, understood that there's no such thing as holding light together. The preceding discussion should suffice to show that one cannot speak of a light quantum that remains undivided and spatially concentrated. My email is here at the bottom. I encourage anyone to contact me. If you disagree, it doesn't matter. I'm trying to find friends here. And also, I encourage you to look at the website, thresholdmodel.com. These lecture slides are my best writing. You can download it. There's all kinds of nice links in it. And I think my hour is up.
Eric, that's amazing. I said in chat, since Greg wasn't here, I was like, let him run over. And I was like, that could be another hour, but
it could be another hour. That's right.
Yeah, you wrapped things up. Yeah. Well, thank you. So let me do this. Let me take down the slide deck and I'll bring everybody in. We need to give you a giant applause, but let me bring the guys in first. Everybody, please give an enormous applause, Mr. Eric Reiter.
Thank you.
Eric, and that was a nice save too, because the audio stuff at the beginning, right, when you're presenting, that can be like, it can throw you. So, excuse me. So yeah, that was wonderful. Okay, so let me see. And do you guys have any questions for Eric? Again, we have lots of time, but you know, we can go to lab updates if nobody does. So. Crickets. Okay. Well,
So I guess just
sorry,
a quick question. So how does your view, does it agree or disagree with quantum field theory in some sense? Because there you have this picture of a field. I mean, I guess you're obviously looking into this deeper sub-quantum view, but how do you make light of your views in you know, since there's been so much progress with quantum field theory as well, like how do you interface with that?
Quantum mechanics usually works, or quantum field theory usually works. I mean, I'm not saying that all of quantum mechanics is going to give the wrong answers. I'm changing the words around a good deal of equations where you could see it in another way, especially when you see wave-particle duality. So does quantum field theory explain wave-particle duality? I don't think so. I've just seen these annihilation operators running around. And they would have to go back to the experiments that I showed. And I'm saying they're inadequate experiments to substantiate their claims that it really is quantized like that. So I'm saying, look at the experiments, the fundamental experiments, and argue with them, see what they did wrong with them. I point out what they did wrong with them, and then argue with my experiments to show the opposite answer. I don't know anything about quantum field theory. I just know a little bit about like what I just said.
Awesome. Yeah. I mean, in some sense, a quantum field, like it can express particle behavior, but still has wave-like behavior. So I don't see it as like a problem to be solved.
It is the problem I solve. How does a particle show wave-like behavior? What are they doing to make it do that? It's a probability interpretation. The probability interpretation says the opposite of what I'm showing in the experiment. So look at the experiment and see how it fits that. No, you missed the point. You missed the point of what the interpretations of probability, how they fit to experiment. The probability and they say so. The people who do these experiments say that it should show up one way or another like that. And they go through all these acts of desperation to change the chance equation to make it look like that. So that's not fair. They didn't do the experiment right. And their theory is based on the idea that the experiment shows up to hold the H nu together. You go back to one of my earlier slides where it's just a model of the photon. It's supposed to go one way or the other. They buy that. That's the problem. Go back to that experiment and see how it's wrong. Then that'll affect all of those other quantum field theory stuff, why they say that, oh yeah, the probability interpretation. Probability interpretation, on the average, would show no peak in the histogram of time difference. That's why they do the comparison to chance. That's why all the other people did it that way.
Awesome. Let me see. Does anybody else have questions for Eric?
Hello, Chris.
Curtis.
Oh,
Curtis.
sorry.
Yes.
Curtis.
No
Curtis.
problem. I've been called worse.
Hello,
But,
Curtis.
Yeah, I just wanted to chime in. I basically, I mean, the way I see it is that, you know, your work really kind of points to a limit in terms of quantum mechanics being, I mean, the big question is it fundamental, right? And if there's a limit to the domain where it makes accurate predictions, then then it's not fundamental, right? So, and that's kind of one of the things with the theory I've worked with in the past, which is an extension of general relativity. In that theory, basically quantum mechanics pops out as a low energy linear approximation. So when you said earlier, like most people wouldn't expect the higher energy to show that there is, the quantum falls, that's exactly where I would look for it, actually, in that theory, where higher energy, you get other effects, and the linear, basically the approximation of quantum mechanics, being a linear theory, it falls apart. So, yeah, definitely, I'm a great supporter of your work. I wanted to be there last week. I've been fighting some bronchitis, but I'm better now. But yeah, I'm really glad you came along. And the other thing I want to say in terms of like what we're trying to do here at APEC, I mean, it's really important if we're looking at these kind of like the edges of technology and what matter does, and how the universe really works. We have to keep an open mind in terms of understanding, what these experiments actually say, and not assuming that quantum field theory or any of these things, really it's experiments that we got to look at this point, because I think there's our understanding has been there's these domains that are fleshed out, but whether they're fundamental or not, there's so much information, and it's it takes time. Step back, think about things, slow down. Really, otherwise, I don't think we're going to understand what's really happening. But I was excited to see what when you showed the particle-antiparticle annihilation and that work. I mean, that's like you had mentioned, that's directly applicable to what we're doing here.
Right. That's how to drive your flying saucer, understanding antimatter.
Yep, exactly. Yeah. Well, thank you, Eric, for giving this presentation. I appreciate it.
Yeah, you mentioned the low energy stuff. You cannot do an energy budget with visible light. You cannot see, well, do those pulses count for an H nu? And when you put them together, can you make the 2-for-1 argument to show the alternative? You just can't do it. You have to go to gamma rays. And there's nothing wrong with using gamma rays. It's electromagnetic and it diffracts. They have gamma ray spectrometers made out of crystals. So thank you so much, Curtis, for your encouraging words.
Yeah, you're welcome.
Awesome. Well, Curtis, thank you. So, guys, I think, do you want to go to lab time now? Should we go to lab time? Okay, well, let's do that. So let's put our hands together and give Eric another tremendous applause. Eric, thank you so much. I'm absolutely overjoyed. If you have more that you want to share, we will have you back in the future too.
Thank you.
Yeah, absolutely. And again, great recovery on the audio issues. And that stuff like that happens to everybody. Cameras and all that. It's just technology. So okay, well, why don't we go into lab time? So what I'm going to do is take everybody out except for Mark. And the reason I want to do that is I know Mark has to bail out, right?
No, actually, I have somebody coming in here in like 10 minutes, and I got a long presentation. So why don't you let somebody else go first? Okay.
So let me see. That would probably be, let me see. I see Drew. Drew, do you want to go? Okay.
Hello. Okay, well, it's kind of a hodgepodge of what's going on in the shop. Today was a serious work on the big chamber day. So I'm exhausted because I've been standing for about 9 hours. So I'm just going to throw some stuff up and show y'all what we've been doing in the shop. If I can figure out how to do that. Share screen and share screen. These are all different things. Why are they different things? Oh, okay.
Oh, yeah. So let me see. If you go to present, share screen, and then it's showing your tabs, right? So it's Chrome tab, window, or entire screen.
Did it happen?
No.
Okay, I pressed all the buttons. It says stop sharing, but nothing is sharing.
Okay, so you might try again. Share screen.
Okay. So present,
Yeah.
share screen, and then
Okay.
there's like follow these steps. Share screen, entire screen, screen 2, share.
There we go.
Oh, okay. That's the same thing as did last time. All right. Okay. So, this just real quick. This is a picture of. This is my camera that looks out onto to me. And it just so happens that I'm not sitting in the chair, but the chamber that we were working on today is back here. This back here. So we were sanding on this bad boy. It's 68 inches in diameter, about 80 inches long, and the 4 turbo pumps are going to get mounted on 2 of these monster flanges up here in the backside. I got lots of pictures of that in a little bit. The cool thing was this test run from, I don't know, 2 weeks ago maybe. And the only thing of any part here is that it started down here at negative 0.7 millinewtons and ended up here at positive 0.7 millinewtons. So that's about a 15 or 1600 micronewton throw. So basically turn it on, goes up 1600 micronewtons in thrust, turn it off, and it comes right back down to a little bit lower than 0. So this is from the peak. Oh, I'm sorry, I'm on the wrong screen. So from the peak here at the top, or actually here at the top, to the trough here at the bottom is about 1700 micronewtons. But in a single test, it was about a 1600 micronewton. This is full on, full off, over a millinewton from a little bit of plastic about this big. So I'm pretty stoked, very excited. Reproduced this test a couple times. So I'm loving those test results. And let's see, on to today, which was all about big vacuum chamber. So this is the large. There used to be some 16-inch diameter diffusion pumps and 16-inch diameter plate valves that hung off of this monster steel. They were about 3 tons a piece, and they were just lethal. So I got rid of all that stuff years ago, and now I'm just converting it all over to turbo. So I'm just going to kind of run through the pictures. This is kind of cool because we had a thing burning in the middle of the thing, and it was very cool. Just working and around. This is the gang. We were kind of assembled and just spent hours upon hours grinding and sanding and blasting away. And this is just grunt work. There's no fun factor in any of this. We covered the floor with just an endless amount of dust, and then we picked the youngest team member to do all the cleanup. So we're just hitting it for hours on end. Cleaned up all the interfaces, got ready to weld on some new stuff, got ready to weld on some plugs. This had this water jetted out of stainless. This is the plate that's going to go on that giant hole. I'm going to put those 2 8-inch, those are 8-inch CF flanges. There's 2 of these entire plates, 1 for each side. So I'm going to be able to hang 4 turbos off of this chamber, and I'm just going to run this thing off of 4 8-inch turbos. Hoping to be able to pump down to 10 to the -6 in 12 hours, maybe. I think it's a little ambitious, but the nice thing about this is if this isn't a regular test chamber, this will be for things that I already know work, and I want to demonstrate them, maybe bigger units. Like if I want to scale up to thrusters that are 10, 12, 20 inches across, easily put them in a chamber this size with no edge effects. So just, a lot of scaling up. This was sort of at the end, and this is all going to get painted with Rust-Oleum just to attack the rust. This is an old carbon steel chamber. So this is from the 1960s. It's an old NCR or RCN or something. So it's bizarre. I mean, this is 3/8-inch stainless, or I'm sorry, 3/8-inch carbon steel, and this chamber shrinks about about a half an inch in diameter under vacuum. It's impossible to imagine a 3/8 inch thick carbon steel shell imploding inwards a half an inch across the outside diameter under vacuum. It blows my mind every time I think about the forces. I did the math once, and there's like I don't know 100,000 pounds of force on the stupid door or something ridiculous like that. So anyhow, this was just a really big work day. Sanded inside, sanded outside, sanded upside, downside, sanded everything. That's it. That was our day. That's what's going on. Oh, and as you saw before, this is our boss, and she was just checking it out, making sure everything is working fine.
Okay. Awesome. Drew, thank you, sir. Thank you for the lab update. So let me see. Let me go to Curtis Horn next. I'll bring Curtis because Curtis, I think you and Jim have a lab update too, right?
Yes.
Okay. Awesome. Yeah, you guys are all crushing it. I mean, it's absolutely amazing. You got all of you and making headlines and news. It's amazing. It's an honor to see this.
All right, thank you, Tim. So yeah, I think last time I was not able to get on, but there's several developments. One is that we have started testing. Jim has been going in and testing different signals to look at the possibility of stick slip as something that is happening with the motion. So we're testing basically different waveforms, and I'll get into detail on that. But in addition, we had a group meeting, and we basically decided that as part of what we're doing, because right now we've been trying to use different rods with different types of bearings to see if we could reduce or eliminate stick slip and get like consistent motion. And what we decided on is we're going to do an alternate experiment. Basically, the core is the same, but what we're going to do is instead of having the device on a torsion balance, we're going to actually put it in. This is a small little vacuum chamber. It's made out of a plastic type material that's clear and meant for vacuum, and it doesn't weigh much. So what we were planning on doing is putting a device in one of these and having that hang off of basically a air bearing. So the device is in vacuum, so that eliminates the issue with most of the issue with air effects. So we're planning on pumping it down and having it in a way where it can stay at vacuum. So we're going to be closing it off and checking that the pressure stays at some value that's consistent in terms of making sure it's low enough vacuum to have valid results. And in addition, it's fully enclosed. So even if there were a little bit of energy, it's hitting the walls, it's not transmitting out. That's very unlikely explanation. Now, that's assuming that something happens. So we're working on getting this device, getting the air bearing equipment, and we're going to be setting this up as an alternate, where we're hoping that we run a device and we get basically a linear acceleration. That would show right away if we're getting that. If what we're doing is just vibrating and nothing mechanically is happening, it's not going to go anywhere, right? So that's one of the alternative things that we're doing. So I mentioned earlier that we have different waveforms that we're energizing the device, and you can see. So I have several examples. The first one here is a sine waveform, and again, you guys have probably seen all these squiggles, but I'll go over it again. On the right, the green is the actual. If you look at this picture, you have the device itself in the middle that's riding on bearings. So the green is the position of that device. The blue is the position of basically the average momentum, and the red is the position of the torsion balance itself that the device is inside. So the green, you can see that once it's energized, you can see with a sine waveform, it kind of moves off and you can tell when there's stick slip when there's a motion and you get opposite motion with the red and the green, and also that the blue is pretty static, right? So you can see here that there is, some stick slip that happens, and then there's actually the blue starts moving, so that kind of tells us there may be, not 100% sure, but there may be a net force occurring, right? And this is a sweep. This is kind of the same kind of pattern we've been doing. This is a sweep from 35 to 20 kilohertz. And this was done at 1.6 to 10 to the minus 4 torr. So this is the sine wave. Here's another test, same frequency range, same voltages used. Basically, this was a 10% sawtooth waveform. So basically, instead of a sine, it's 10% up and then 90% down. So it's kind of an asymmetric sawtooth. And so you see that it behaves a little bit differently. This is a 50%, which is entirely just a symmetric kind of triangles up and down. And you can see this one shows a little bit more of a kind of a smoother. There's like a short stick slip, but then we get that motion, the blue moving pretty much right away when the power is engaged. And then here's the 90%, which kind of looks like it's doing the exact opposite of the 10% or the 50%. So it's like, a little, we're seeing some differences in the symmetry of the waveform. So we're currently analyzing this data and, basically trying to eliminate or reduce the stick slip effects in our experiment. So that's about it in terms of lab update. I won't talk about theory today too much unless somebody asks. So I'll end it here.
Awesome. Curtis, thank you. Thank you again. Thank you so much, man. Okay, let me take down the slideshow and actually, let me see. I think Mark is still working on his thing. If it's cool, I'll do a quick update as well. So I'll just show everybody this. So as you guys may or may not know, because we're live casting on a couple of different channels here. Let me see if I can do this. There we go. So this is my Flickr photo gallery, and I will drop a link into this for everybody. So, I've been traveling all year. We've got arts parts, SEM analysis. That's pretty recent. We just added some more to that. Metallurgical analysis. This is brand new, so I'm going to start with this. So I'm just going to run you through it really quick. Jared Yates will probably do a larger presentation on this. So he was doing metallurgical samples at the Falcon Space meetup that we had last week. And so I'm just going to quickly run through some of these samples. He found some interesting, what looks like, I believe he said they were similar to tin whiskers, but the geometry of them seemed very different. And again, this is a bismuth magnesium sample. He ended up comparing this, I believe, to bismuth or to magnesium orthosilicate, and it did not show any of these. So these little strands here, and you could see them in some of these photos, are very unique. Apparently some kind of crystal structure or microstructure in the arts parts. Again, that is the purported UFO, UAP material. What made this possible was an upgrade to the microscope. We have, I believe, an 18 megapixel camera now hooked up to the metallurgical microscope. And so using this equipment, we were able to get these. We've also continued to do chemical analysis. Let me go back to my albums list. For anybody who hasn't seen this, we did scanning electron microscopy on it. We're also doing some other lab tests as well. So what we're trying to do is really dig in here to arts parts and go beyond what's been done in the past. We're confirming a lot of what was found earlier. Travis Taylor has done analysis on these. Oak Ridge National Labs did one last year. It appears that we're finding some things in our sample fragment that they didn't find. So I just wanted to let you guys know about those. And again, I'll drop a link into chat for this. The other thing I wanted to show you was This was like an all-week project for me. I shot thousands of photos of our lab meetup, and I'm not going to scroll through these one at a time, but you should be able to see them on the page. This is a lot of the regulars from the APEC conference. We all got together at Falcon Space Labs in Hawthorne, New Jersey, and we did a lot of B-field Brown testing. As you guys know, Jesse Michaels has this prize that he put out there for B-field Brown, and so we were all kind of going for that. So my role there, because I was not doing a lot of hands-on work, was basically just taking photos. Actually, there are a couple of photos of me here. There's one. So as you guys may know, I worked with lifters in the past. They had some B-field Brown stuff that was similar to what I've worked on, so I just worked on wiring it up. There aren't good photos there. These are Campbell thrusters that I'm working on, and it appears to be kind of a type of B-field Brown. This gentleman flew in, Alexander flew in from Portugal, and you can see the Campbell thrusters that he brought with him. So he actually has some unique things that he's done with those. And this is the vacuum chamber that Mark so kindly put together for us. But again, we had the whole crew there. We had Kurt Zeller. Down on this page, you can see Mark. You can see David Chester, Kurt Zeller in the tan shirt there, Jeremiah Pop over on the right, Jared Yates, Michael Perrone, Tom Butler, the whole crew. And there's Wayne and Charles Crawford III and lots and lots of folks. So again, I will drop a link into chat there, and that is kind of what's going on for us. Oh, I will do this. I am also in the process of updating the Falcon Space website. And so, again, Falcon Space is not a part of APEC, but Mark is co-founder of this conference, and he basically got me to work on his website a while ago. And so I have been just trying to do some updates there, especially working on the text. The other thing that I got, there's a video on this page. We reshot some of the videos about dynamic nuclear polarization, and we added in some stuff about arts parts, and I added in some behind the scenes photos, and just links and recent news appearances as well. So I have a little bit more work to do on this, but I wanted to show you the Falcon Space website. Again, I will put a link in for that as well. So I think that's what I have. And it looks like Mark Sokol is there. Mark, do you want to do lab updates for us?
Yeah, I'll give you guys a quick update about what's happening over here. So this is the same thrusters that you were balancing the other day. And we have this in a, right now it's -5. It was at -6 before, but I think there was a little bit of outgassing. But the chamber has been flushed with sulfur hexafluoride. So up over here, there's actually a bag of sulfur hexafluoride. We fill up the chamber with sulfur hex and then pump it back out into the bag to reuse it for another time. So the small amount of molecules that are in there are actually extremely inert gases. And as far as all the people arguing this might be ion wind would actually make this device spin in the opposite direction. And we know that because when we fill it up with air, or we put a little bit of air into it, it actually spins in the other direction, much more violently than it's spinning in this direction towards the tube. But here it is, it's running. We're at about 1.5 milliamperes, and I think it's around 30,000 volts. There's a little bit of arcing over that's outside of the chamber. But this is what's happening with it right now. We can shut off the light. Okay, so what's happening right now, it just came to a stop. This is exactly what I wanted to show you guys. So the outgassing and just pressure from the air getting into the system has finally allowed for a breakdown to a point where it starts doing the ion wind thing. Yeah, so we're losing our vacuum right now, and it's starting to come to a stop. And if I were to open a valve, for instance, what you would see is it starting to rapidly rotate in the opposite direction. This is exactly what I was trying to show everyone. There you go. Yeah. Yeah. So nothing was changed on my side. I didn't change anything. The only thing that has changed in this system right now is the pressure in the chamber is rising due to outgassing. So when you, just like your hair goes flying out when you apply high voltage, the same thing happens to devices in a vacuum chamber. Little particles get thrown off from the high voltage. And there you can see it's rapidly increasing in speed. This is more likely due to ion wind. Now it's spinning in the opposite direction. And I have found in the past, it will spin so rapidly in this direction. When viewed from the top, I guess this would be counterclockwise. It would spin so quickly in this direction, it will start to tear itself apart. But that is the ion wind side. The opposite direction when it was going clockwise, as viewed from the top, that was an anomalous thrust, probably similar to what the Bifield Brown effect is. There is some changes or DVDTs in the voltage over time. I don't think those are really related to the effect, especially not when it's ion wind. But that happens because of there's like little breakdowns or bad connections with the system, so you get short spikes in voltage. Now, in terms of the actual voltages that we're seeing here, yeah, it's around negative 25,000, and top to bottom is 17,000 in the peaks. So it's not going all the way back to zero. It's going between 25 and 10,000, something like that. And those are just miniature spikes from bad connections between the pin and the ball on the bottom. But what you're seeing right now, this is definitely ion wind. It started spinning in the opposite direction. The pressure is starting to slowly rise up. We're at 5 to -5. There's probably outgassing going on. If I were to shut this device off and let it vacuum down for another hour or so, get back to -6, back to -7, that's the area you really want to be in to get rid of ion wind at these voltages. We would start to see these forces that go in the opposite direction of ion wind. So I'm going to shut down the high voltage over here, and maybe in the after party we'll be able to give you a demo of it spinning in the opposite direction again. Other things that we have going on over here at the lab. Pinky's just saying hi to somebody. So the S-band Alzaphon, Pinky, she's excited. So the S-band Alzaphon is actually finally set up, although the vacuum pressure gauge is a little defunct. We have a sample in there right now. We're pulling down a vacuum on it, and or we'll be ready to run this in the next weeks or so. There's a couple more fine-tuning processes that need to be done, but for the most part, this thing is up and ready to go. And I think that's it.
Awesome. Mark, that's amazing. You told me about this. You actually told me about this last week. This was something that you observed, and I saw it too, but I didn't place the significance on it. But you just demoed that. So
yeah, that was complete by accident that actually happened. The timing just was perfect. But yeah. I've observed that before, and that's what I believe is happening. If anyone in the comments wants to give us another explanation as to why it would do that, spin in one direction, and then as the pressure rises, start spinning in the other, I would love to hear it. And I got balloons.
Yeah, hand gestures. Hand gestures. Yeah. This is AI. It's going to take over the world and throw balloons at us. That's so,
okay.
Yeah.
And Michael Perrone, I think, has an update as well.
Okay. Yes, I see Michael waving. Okay, let me bring Michael in. Although, so what I'm going to do is, sorry about that. Okay, sorry. So what I am going to do is put that video up online, and I'll cut that segment out because I think that's important to put it up by itself. I mean, to me, it looks like he just demonstrated the difference between B-field Brown, and ion wind. One thing I did want to mention, and this goes from our testing last week, I have never worked with B-field Brown in a vacuum chamber before, and I got to work not only with Mark, but with Jared, with Alexander, with several different people. Pretty much everybody attempted that vacuum chamber. One of the things that surprised me was there's this idea that if you take any kind of B-field Brown device, right, like a lifter or a gravity capacitor or the Campbell thruster or anything like that, you put it in a vacuum, you turn up the voltage, and it will either work or not, right? It's supposed to be this clean, precise test, whereas in the normal atmosphere, you get ion wind. What I found was the vacuum chamber is just as messy as anything else. And so, like what Mark demonstrated was, when you first pump that thing down, you do have 10 to the negative 7th torr. That's where we were operating most of the time. You start to get outgassing that the fields create. A lot of it is wire erosion. You get electrons that are like thermally ejected from the wires. So even at those incredibly low pressures, you start to get metal ions filling up that chamber, flying around. And it just makes things really, really complicated to work with. So that's just kind of something to keep in mind. For me, that was a giant learning experience. Ion wind it looks like that's just something that you have to deal with. It can be shielded against, and that's something that we'll work on in future experiments. So I'm going to bring Michael in. Michael, take it away, sir.
Hey, Tim. So, if anyone's been paying attention to Jeremy Reese's channel, we posted some videos 2 weeks ago. We've had a replication of Daniel Sheehan's bipolar membrane experiment, and it's going well. So actually, at first, let's see. So you've got these. You have a reservoir of liquid on each side. This part on the inside it can be inserted. So then these clamp together around bipolar membrane like this. And we cut some small holes for flow back through that. And we assemble this whole thing together with clear plastic. There's nothing in the plastic that's out of the ordinary. And then we put a very dilute salt solution in that, sodium hydroxide in our case. We're going to try a few others and a few different types of bipolar membranes. In any case, the experimental setup, if you can.
Okay, it looks like we may have just lost Michael's feed.
Oh, I think I got. I'm
back. Are you back? Okay.
Yeah.
Okay.
How long was I gone?
Oh, only probably about 15 seconds or so.
Okay. So yeah, basically we put the thing in a black container to keep any light out in case there's photocatalytic effects. We've been keeping this thing dead shorted for the past month or so. So initially it fell by a factor of 10 or something. And now it's settled around 0.015 millivolts. It changes with the temperature over the course of the day, which is exciting because it should be temperature dependent. So what I think we're going to try is the next test would be to heat this up and cool it down and see if the voltage varies accordingly with temperature. If there's any chemical energy left in there, then the chemical energy would initially go up with temperature, but then it would get used up faster. So it would be an accelerated aging test, sort of. So if I short this here, it varies a lot too. It's like a statistical phenomenon. But you short that, and then it will slowly climb back up we're talking about like fractions of a picowatt here. It's tiny. It's amazing that the scope can even pick it up, but it's not zero. And after having it dead shorted for 2 weeks, it has leveled off at about 0.015 millivolts. So that's very interesting. And yeah, if you just keep it there, it'll slowly work its way back. And the bias on this Keithley's like about 10, maybe 20 millivolts at most. So if I switch the leads, if I can, yeah, so it's 80 instead of 100 at that. So yeah, about, let's say 20. In any case, not a lot of power, but it's very persistent, and more tests on the way. Is anyone there? Well, I mean, that's about it. So, I mean, we have a variety of these devices that we'll try to use some different materials, different bipolar membranes, and then we'll go reach out to Dan Sheehan. He's got something that he considers economically viable based on a similar principle. So we'll talk to him about that. I mean, this one, it's difficult to see how you scale this particular thing up economically, but perhaps he has a new idea that's a slightly different arrangement and that just puts out a lot more power. The interesting thing about this is you're just taking thermal energy and you're turning it into electrical. It's I mean, it's non-equilibrium steady state statistical mechanics, I should say, taking advantage of some non-ergodic behavior in bipolar membranes. Anyway, yeah, it's just that's where that is, and it's cool to see. I mean, we need to take more data. We'll be doing a lot of data acquisition over the next week, but yeah, there you go.
Yeah, Michael, thank you. Thank you. So for folks who don't know, right, because not a lot of people have been following this experiment closely, you are working on, you could almost call this a source of free energy, or you could, it's basically a second law violator, right? But what's exciting to me is you've been working on this for a very long time. You guys are wrapping up this project with a positive result, right? You're like, okay, we did it, we're there. And so now what we're looking at is how can you take that further? And I know that you've been in talks with Dan Sheehan and some of his colleagues as well, so that's really exciting. It's really exciting.
Yeah. Yeah. And I mean, there's two things also, like this might be an improvement on Dan Sheehan's original design from his experiment, because he was using silver chloride, which there's some issues with that. It photo degrades and things. This uses carbon nitride, which is still photoactive, but that's why we enclosed it in a black container so that no light's getting to it. And we're still seeing the effect without the silver chloride present. So that's really exciting. It's encouraging. And yeah, I mean, it seems it's legit. I mean, I think I'd like to do a little more due diligence before like publishing a paper on it or anything. But yeah, I mean, Vladislav Kapek's book, just want to give that a shout out, with Dan Sheehan back in the day. He worked out all the math for this, for non-equilibrium steady state systems that can do this sort of thing. And I want to stress, it's not really violating the second law, it's avoiding it, because the second law is derived, unlike the first or third law of thermodynamics. So you need ergodicity and weak quantum mechanical coupling, and it's known in biological systems and elsewhere that weak coupling is not always true. So the foundations undergirding the axioms underneath the second law are on shaky footing, not necessarily like anything that where those are still good assumptions still operates under the second law of thermodynamics. This would be a superset or an unexplored corner of thermodynamics. So
and while you're going over that, so this is your website, Sanrel LLC, and people can just Google that, right?
For this particular, they can certainly do that. Thank you for the publicity there, Tim. And
oh yeah,
absolutely. I would recommend. If anyone wants to try building these themselves, it's quite repeatable now. So we have a Hackaday page as well. I can post the link if you're.
Yeah, if you'd like to. Yeah, if you want to post that link. So this is the Hackaday page. This is where you're open sourcing a lot of your ideas, right? And
that's my website. The Hackaday page I just posted in the chat here. So you can
wonderful. Okay, I'm sorry about that. Okay.
Yeah. Perfect. So that has instructions on how to construct these things, and we'll be adding to it over the next week. And so we encourage researchers to give it a try, give us some feedback. This initial one is like fractions of a picowatt, so posting it online like this, it's not going to like, at least for Dan Sheehan's team, they claim they have something that can put out watts to kilowatts. So I'm excited to potentially talk to them about that. But this is just picowatts, so I'm sure if it's open source, they won't mind. If anything, it'll allow more people to replicate the result themselves. And for something controversial like this involving the second law, that's important.
Okay, and I just dropped the main Sanrel LLC link in chat there, and I think you may have just done Hackaday, but
it's in the StreamYard chat.
Oh, okay. Okay, so you'd put that in private chat. I am just dropping that in public chat. So that is forever embedded in our live feed notes. So
you could also just show off the site too if you want that.
Yeah. If you want, actually, Michael, do you want to share that and walk us through it? I think we have extra time.
I guess. Let's see.
Yeah, but bring it up. So it's the present button down at the bottom of your screen.
Just share screen.
Yeah.
All right. It's where'd it go?
Okay, so then there's a share screen. So there's a little pop-up. Share screen.
There we go.
Yeah.
Cool. So
there we go.
That's yours. Yeah, awesome. So we've got a Hackaday page here. We got some other projects too. Metal printing stuff that's old. Haven't touched it in a while. Very tricky stuff. Ceramics. This is a really cool one as well. All sorts of stuff on the way. Bismuth magnesium things that's on hold for now. But then there's our design for the, I'll be posting more for the Townsend Brown replication. Hopefully I can get back down to Mark's place and test the thing at higher voltages just to give it the best possible chance of getting a result out of that system. We have a very close replication to we have something resembling Drew's device that he showed off, Tim, on your channel earlier, that we'll post some build instructions for that at some point too. But yeah, there's a lot of cool stuff here. Work in progress, of course. And then for the bipolar membrane thing, it's the most popular thing at the moment. A lot of engineers have already been watching us on this site. And there's just instructions and STLs, 3D models, resources, logs, and instructions and files. And we'll see about posting it on GitHub. The GitHub's pretty empty at the moment, but getting somewhere. This older design is not the current design by any means, but that's also pretty cool to try. You can just take a pH gradient. You can put an acid and a base on the two sides of this, and it'll produce a voltage across it. Anyway, that's good. Let me see if I can stop that. Yeah, there we go.
Okay, awesome. And you know what? While we are sharing screens, just because, again, I'm broadcasting on different channels. I've got this up on my Twitter feed, and we have a lot of people watching on Twitter right now. So what I'm going to share is the main alt propulsion website. If you haven't seen this, it is just www.altpropulsion.com, and I will drop a link into chat there. People see the actual presentation on different channels. So our website, basically, we have a collection of presenters. We have bios for presenters, as well as all of the events. December 21st is obviously still coming up. This is today's event, and I'm actually going to replace this with the video. So you can go to any of these pages and watch past presentations on the page itself. We also have Zoom calls. Basically, we alternate. So we'll do 2 weeks on, 2 weeks off kind of a thing. So it's for every 2 weeks we do a webinar, and then 2 weeks later we'll do a Zoom session, and we upload those after the fact. So this is the Alt Propulsion website. And we've had, I think we're at like 66 or 67 conferences so far, you know, over the last few years. So it's truly been an honor. It's been an honor to you know, work with you guys and see all the progress and see this community come together. I mean, for me, it's a community effort. So let me bring the guys back in here. I guess we could just do open discussion if you guys are okay with that. Yeah, and Michael, thank you again. Thank you again. So yeah, there we go. Woohoo! Open discussion time.
Good work, everyone. So Drew, we were able to test the devices, and well, I mean, I wasn't able to get the voltage high enough, so I'll go back down and put 50 kilovolts on that thing and hopefully get it to work. Also,
Yeah, I was noticing. I put a note in the private chat, but it sure looks like Mark's toy. When there's low pressure, with low vacuum, it's ion wind. You're just spraying gas off the end of that metal tube. But when you get the high end of it, and you're spinning in the direction away from the metal tube, I don't know what that would be, counterclockwise, I guess, Mark.
Yeah, when it goes towards the tube, that's in high vacuum. When it goes towards the pointy end, that's in low vacuum.
Yeah, right. I got a feeling that the high vacuum one is not the pin and plate, or the comb and plate, where you would go towards, you know, this is the small surface area and this is the large surface area. It's not that. It's the one where you have material between the high voltage, or the small area, and the plate, and you're actually doing the thing that only Charlie understands, the div effect or something, div. So it's the gradient. You're passing the gradient through the material.
A.
Excuse me?
Divergence of A.
Yeah. Well, yeah, whatever that thing is. Only Charlie understands that, as far as I can tell.
Wow.
But that is the divergence of A is about an order of magnitude or more, maybe 2 orders of magnitude stronger than just the pure electrostatic pressure version of it. So, although it's a whole lot less charge involved, the forces are just ridiculous. They're 2 or 3 orders of magnitude greater. So it's an astounding thing. But it's very tricky because you're passing very high fields, 10 to the 6th, 10 to the 7th, 10 to the 8th volts per meter through material, and all kinds of mischievous things happen. Things outgas, things arc, spark, sputter. But the thrust of that div A is opposite the thrust of a standard electrostatic propulsion system.
And it's also opposite. It's opposite the ion wind, which makes me say there is something going on there.
Drew, I was incredibly surprised at how messy it is inside of that vacuum chamber. I'd always thought, from all of the reading and literature, right, that, you know, they say vacuum is the holy grail, you know, because it's pure, right? Because nothing is flying. But no, there's stuff all over the place.
No, it's a mess. And one little curious thing that I didn't believe until I ran the test is when you turn on an ion gauge to see what vacuum level you're at, an ion gauge is dumping ions into the chamber. You think, well, who cares? My system is sensitive enough where switching on an ion gauge from its cold state to the on state, over the next 15 or 20 minutes, I can actually watch a false 500 micronewtons of thrust be generated in the system from all those ions flying around, sticking to surfaces, messing with things. It's not really false thrust; it's thrust that wasn't expected because those ions are sticking to all kinds of weird surfaces, and they're causing, they might be sticking to the outside of the ITO shield box, and all of a sudden you got Coulomb attraction, you got all kinds of mischievous things going on. And then you turn off the ion gauge, just turn it off. And over the course of the next 30 or 40 minutes, the thrust comes right back to where it was. So it's real easy to do this wrong. I mean, it's depressingly easy to get false data at these thrust levels. And, I'm talking millinewtons of thrust. And still, it's easy to get false data.
Well, I think one of the other things that's important, we should point out, Drew, you guys have a patented effect, and your partner, Charles Buehler, Dr. Charles Buehler, is the NASA electrostatics expert. So, I mean, you could argue, I would argue, that there's probably nobody in the world more qualified to do good, rigorous tests. And certainly nobody is going to be more aware of some of the ways that it can fail than him. And then for yourself, you have been doing incredibly detailed vacuum chamber work for like decades now, right? So what you guys have as a team is probably the absolute best that's out there. And I think a corollary there is that when other people do tests and they're like, oh no, it's this, I can rule it out because of X, Y, and Z. There are so many ways to get false data, as you've mentioned. Yes. It takes.
Totally agree. That's why I'm very impressed with Mark's rigor. He's applied the engineering principles and the scientific principles and stuff we've seen over the years. Stuff he's just never seen before. He's getting into brand new regimes of pressure, brand new regimes of vacuum, brand new regimes of material sciences. Materials vacuum is a horrible place. And you're using very high voltages, by the way, so you're actually sputtering metal. When you get that pressure low enough, you're actually blowing metal off that metal tube. So you're literally depositing whatever that copper, I don't know what that material is, but whatever it is, stainless, you're depositing it on the walls of the glass. You are slowly electroplating or whatever it is, sputtering the material right onto the walls of that glass and making it slightly conductive. So it's just a miserable experience. And then to that you've got a great big seal at the bottom, which means you got to put a little bit of lubricant on it or something. That lubricant's going to trap moisture. You're going to get outgassing forever. You got a hodgepodge of materials in there. All of them are outgassing. All of them are emitting all kinds of mischief. So it's an exercise in rigor. And
what really helped me out was talking to you, Drew, and you gave us the roughing pump for this as well. And you told me everything that will go wrong, and all those things did go wrong. I also talked to Charlie Buehler about it, and I ran the idea of making that spiral with him just to overcome the Coulomb attraction. We did try it with a straight line up, Tim, and it just got stuck on that, right?
Yeah, I Drew, thank you for that. That was
you're quite welcome. I've been working with Michael, try to helping him along, and we want to see our technology reproduced. And as the patents catch up to the patents that we have we have a whole bunch of them in the cycle. As they catch up and they get released, we'll be releasing the how to build the new stuff. That way you can reproduce the new stuff, because the new stuff is, I don't know, 10, 20x the thrust level, the old stuff, and it's much more elegant. So just we're playing the game because we've got so many people trying to jump the claim on us that it's just getting ridiculous. But Mark, did I notice you have two of those spirals running in the chamber now, or did you add a second one or something? Or
No, we didn't add a second one yet. No, it's
Okay,
still one.
So actually, I can speak to that. I ran the. This is my mistake. So this is my hands-on mistake. I'll fess up to it. Mark started with an unshielded spiral, and in some of the early tests, one of the things that I noticed, Drew, like you talked about with the sputtering, so it was sputtering from the edge of the Campbell thruster out to the spiral. And so I saw that in the early tests, and I said, okay, maybe we can solve this by running a wire straight up the side of the chamber and using shielded wire. And that was a mistake, because then what happened was the Campbell thruster would basically, the sputtering stopped, but it would rotate towards that wire, and the Coulomb attraction would lock it there. And so then number three, and this is where your advice comes in, because Mark said, here's what the problem is, it's Coulomb attraction. He said, run another spiral, but this time do it shielded. And so that, combined with pumping it down and making sure it was at 10 to the negative 7th, solved the issue temporarily. But again, one of the things, Mark just demoed this a few minutes ago, is when you run this thing over time, your temperature goes, or your pressure goes from 10 to the negative 7th back up to 10 to the negative 6th. And that was something that we struggled with. So.
yeah, with those voltages will actually cause materials to outgas.
Yeah.
But I see James Woodward on. Are we doing something with that vacuum pump? It's still sitting on a pallet, ready to go.
Jim, you're muted, sir.
Curtis all the way along, and I would be crowding him right now.
There's Curtis.
Hello, Curtis.
Let's yell at Curtis. Curtis, vacuum pump, sir.
Yeah, we're looking for a shipper that'll meet your criteria. So we've been having trouble getting contact with that.
Sure.
One shipping company.
Again, pretty much any day after 6 p.m. or 5 p.m., even 5 p.m., any day after 5 p.m. or any time on the weekend. And there's a second one of those pumps up to a good home. And if anybody wants any big diffusion pump stuff, they're welcome to all the diffusion stuff I took off the chamber. Those are 8-inch diffusion pumps with full vacuum stack.
We got an Agilent 304 turbo pump.
Yeah, everyone wants a turbo. You do not want a diffusion pump.
No, the oil's very, very expensive.
It's very dangerous.
Yes. I used to use diffusion pumps 30 years ago and had a laboratory accident where the cooling system on the diffusion pump broke down over the weekend. And it was a hell of a mess to clean up and very expensive. So turbo pumps, not diffusion pumps.
Yeah, that's why they're free to a good home. The pumps are the mechanical pumps are fine. They're just older generation. They're big, loud, clunky, and they got all kinds of they got the wrong interfaces for all the high, all the new stuff.
If I could add this in, and I think this is important to point out, is, I've been in this community for 25 years.
Tim,
now.
I think your mic is down, Tim. I hear Drew fine. I hear Curtis fine.
Oh, is my volume might be down?
Your volume mic is down.
Okay, let me see. I will. Let me go into.
While Tim's doing that, Drew, we're doing our best here to get everything set up again for another go with those tests. So we have everything set up exactly to your specifications, and we're pretty much ready to go again.
Is this better, guys?
Yes.
Sure, Tim. Yeah, I can hear you.
Better.
So what my thought was, I've been in this area probably about 25 years now, and I think one of the things that I've seen is there have always been isolated groups that have had good test equipment, right? Like the folks who tested the lifters, they were over in Huntsville. They were able to get a vacuum chamber. I think they rented one. I don't think they had one. But what I'm seeing now is this community itself has an increasing number of vacuum chambers, high voltage equipment, right? Good working equipment, good measuring equipment. And so for me, that's really exciting and encouraging, because it used to be, right? It's like, again, hey, let's test this device in vacuum. Do you know anybody who has one? Well, okay, we can't afford $1,000 a day to test here or there or the other place, you know? And now, like, again, I mean, Mark built a pretty remarkable chamber. Drew has absolutely breathtaking chambers. You know, we have a community that is pulling these tools together and using them. And that's just amazing.
Yeah. Drew, for your big chamber, I would highly recommend that you get roughing turbo pumps. So for every big turbo you got over there, get a medium size turbo on the outlet of it before it goes to a roughing pump. That will decrease your pump down time by about 75%. So instead of 24 hours, you might be looking at 6 hours or less.
All right. Yeah, I've got a small turbo pump. I was gonna gang all 4 of them together, run them into a header, and run it down to the scroll. I have a new scroll pump. It's super scroll pump. So I was gonna do that, but I could always run it through the little turbo that I have. So I actually use the turbo as a like a roots blower in front of instead of the pump. But I just wanted to mention to Tim that my chambers are available. If we pre-coordinate. Of course, I live in sunny Florida, so you'd have to come here. But I don't charge, and you can't squawk. But I am more than willing to put someone's experiment in the chamber and set it up and run it safely, so that they can get some data, whatever. And aside from the cost of visiting sunny Florida and going to the Space Center and having a great day, the test would be free. So I want to offer that to the gang, of course with pre-coordination. But I've spent the multi-$1,000s a day on other people's chambers, and it's a nightmare. It's a nightmare. So
yeah. Well, Drew, thank you.
One last question came to mind on my end. Drew, what do you recommend in terms of like balancing the devices? So like, should we have like some screw thing that we can screw in the XY plane and adjust the balance that way? Or I don't know if we were just like hanging lead weights off of things wherever, try and get it perfectly balanced. It's not easy.
I forgot. You're just building 2 plate thrusters,
just one with
a single with a counterbalance.
Yeah.
Yeah, we used to use we did the same thing. We would put the high voltage equipment, because we were using little micro Spellmans back then. So we just use all the high voltage stuff as the counterbalance.
That gets you most of the way, I guess. Yeah.
You do want to minimize the mass of the structure. Lower mass is always better. But you're talking about running this thing in Mark's chamber, and he brings his power in. So all you have is a little tiny frame, right?
Well, yeah, because so actually I am building. Well, I have a half-built 50 kilovolt source that I'll be attaching and trying to use that by like pumping in 12 volts from the bottom coaxially, and then if that
Michael, can I show what you have over here?
Sure. Well, so I don't know. There's some features of that Drew said to keep private. I think that's their more current stuff. We can show the.
That's shielding on it. That's
a yeah. Oh, careful now. There's is the gallium part removed?
Yeah, the gallium part is down over here.
Oh, okay. Cool.
Yeah.
Well,
just so you guys know, Michael has shielding on the outside.
Shielding is very important, guys. I know nobody likes to play with that, but I strongly recommend, like, that's got aluminum foil all over it. That's a very good idea. The aluminum foil is a nightmare for things arcing and sparking and sputtering, but without some kind of Gaussian shielding or Faraday shielding or whatever we're going to call it, you are begging for false Coulomb attraction to something else.
Yeah. Mm-hmm.
So, and that's been our Achilles heel the whole time, is we have always put shielding on everything. Now, we personally use indium tin oxide on PET it's just called ITO. Indium tin oxide. It's just a clear coating. It's on every one of your phones. It's on every LCD you've ever heard of. It's how you get electricity to the signal to turn on the different pixels. And it is an astounding clear metal. Okay, it will shield your pieces parts indefinitely, and it will put all of your question inside of a Gaussian shield, and that just eliminates the whole Coulomb attraction, because everybody wants to tell you it's Coulomb attraction. So, Mark, what are you spinning there?
Coulomb. So this is actually my version of what Michael built. The gallon stand will go in here. High voltage is up here. This was machined out of a solid block of Teflon. That's what it is. And I inserted a little chamber down there. So gallon stand's in here. High voltage is coming out the peak, which connects to this little brass thingamajig. And then we'll have wires going through the Teflon cup for ground and high voltage up here. So this will be the self-encapsulated spinner.
I really like the design, Mark. I was actually I haven't seen it before today. I mean, I think I saw a prototype earlier, but yeah, I really like, because this any high voltage thing on a power line, you'll have that sort of shape to it, and that'll block.
Yeah, well, the point of this is to increase the surface area between the high voltage and the ground. So
yeah,
it would have to go back and forth through all of these in order to.
Excellent.
What is this thing again?
There's a high voltage contact at the top on a tungsten pin, and then at the bottom we have a pool of liquid metal gallon stand, and then we have a nickel contact that goes in the gallon stand, and that's ground around the outside.
Yeah, basically it's a low friction spinning device that doesn't include another wire going to the top, so we can get rid of all those wires around the.
It's a coaxial high voltage spinning balance.
Is it supposed to self spin?
No. It's
a test rig. You'd be putting the carousel arm on top over here and.
Okay. So that's just some sort of it's just a way to get the positive and the negative into the toy.
Into the toy from the bottom. Yeah. Only
that's
feeding it from
interesting.
the bottom.
You're going to be okay. We're getting into contamination control, and I know y'all don't love that either. But you need to take that whole thing and stop touching it. It needs to be
I need to do a lot more than that.
And I mean completely degreased with acetone degreased.
Yeah, okay? I know it's not ready at all.
Yeah.
This is going to be.
And if your voltage, your voltage goes above about, I'm going to say above about 10 grand. I promise you that charge will crawl along that. You will charge that thing up like a capacitor, because that Teflon is insanely chargeable.
Do you recommend Delrin instead?
We use Delrin for everything. Anytime we're passing through, we use Delrin.
All right.
Just because that stuff is too it's just too easy to charge up Teflon.
I gotcha.
It really is. I know it's a wonderful material to work with. It's a wonderful material to machine. It's friggin' inert. It's a little hydroscopic, but
so for the center rod, would Teflon be okay, or do everything need to be made out of Delrin?
Well, you're probably going to need a metal rod to conduct the current. Is that what that's for?
Well,
I was talking about this part. This part, this is basically the shield between the high voltage and the ground, and then the other part goes on top of it, which.
I mean, you can give it a try, but what's going to happen is, do you have a field meter? Do you have a volt field meter?
Yeah.
Yeah. As soon as you run that thing one time, throw a field meter on it, and you'll see what I'm talking about. You'll probably have 20 kV on that thing.
Well,
you'll have charge on that Teflon, 20 kV easy.
Oh, you're saying the Teflon would never discharge?
Right. The Teflon will never discharge once it picks up some ions. It'll just stay charged, and you think, okay, who cares? It's just, a couple of atoms here and there. No, it's trillions and trillions and trillions. It's nanocoulombs. It's an insane amount of charge that you can pack up on Teflon, and every one of those little ions is generating a field, and every one of those fields wants to find its partner in life and end on your test device. And all of a sudden, the fields on the test device that you're expecting to go where they're supposed to go are going somewhere else.
But Drew,
they don't.
the spinny
Yeah.
outside part's supposed to be ground, so it's enclosed. The high voltage is completely enclosed in ground there.
So that's a giant ground passer through it?
It's a giant coaxial contact.
So the inside's high voltage and there's ground around the outside?
Exactly.
Good luck on that.
We'll see.
I don't know. It might work. I'm just telling you, if it's Teflon, it's going to charge up.
Well, Drew, it's important to mention also, this goes back to yourself and Dr. Bueller's work. You guys are working at much lower voltages, and so you're not going to have a lot of these false positives, right? You're not going to have the sputtering and things like that.
Yeah.
I got Delaware in here.
We played, trust me, we played it. We were at 180,000 volts when we started. Worked our way down rapidly because mostly we were tired of threatening our lives. But once we dropped below 40 kV, the 40 kV range was still super dangerous. Then we dropped into the 20 kV range, and now we're down buzzing around 9.5 or something. The false negatives and the sputtering, it went down. So now, I mean, we have an ammeter on the system. So if I see anything above about 10 microamps, I know there's a short, and I know we're making metal, and we're blasting ITO off of the plastic. If I see more than 10 nano or 10 microamps, I shut the thing down because we're leaking somewhere or something bad.
Awesome. Thanks for all your expertise with this, Drew. It really helps.
Again, I want to see y'all succeed. I want to see more cool videos like Mark's got. I want to see that thing you're building. I want to see that thing spin like a top. Because then I'm going to reproduce what you did in my chamber.
As long as it's in the ground enclosure, the ITO windows don't show anything that's proprietary, so you could show that off if you want on the front. We do have an ITO window on that ground enclosure that we put there. We found some nice copper tape for that.
Yeah, I mean, ITO is a wonderful material. You can tape it together with Kapton tape, and then just run little connections between them. There's no secret sauce on the ITO, and it makes everything transparent to what's going on inside. So there's not some secret box. It's only the magicians know what the hell's going on. That's why we put everything in ITO. We put portholes in our chambers. We want to be able to look in there and see where the sparks are going.
Yeah, that also helps debugging, I imagine. Yeah,
it really does, because when you turn the lights off and you see the purple haze of death, you screwed up. Oh, by the way, that purple glow that you see in those chambers, that's making soft X-rays.
Yeah, we had a Geiger counter over there.
Keep that in mind. Real soft. I mean, they're soft X-rays. Don't get me wrong. You're not cooking yourself or anything, but you ain't helping yourself any either. If you can see it, it's making X-rays.
Yeah. Just like any old cathode ray tube. Yeah.
Y'all ever done the Band-Aid trick in the bathroom?
Yeah, that's fun.
You put the two Band-Aids together and pull them apart, and the lights off, and you see that line of purple when you're pulling the Band-Aids apart. You see that line of purple as you pull them apart.
Yep.
Those are soft X-rays.
Well, I mean, UV and also soft X-rays.
Yeah. You're supercharging the nitrogen that's in the air, and you're basically fluorescing the nitrogen. But that's hitting it hard enough to generate X-rays.
You're making me think of if aliens use a Band-Aid drive to get through space now.
A couple of guys at MIT built a mechanical X-ray generator. Put two spools together that constantly spin, and it's got like two tape spools, and they were generating enough X-ray power to X-ray their hand.
That's amazing.
You're bored.
Well, I think that's probably about it for today, Tim, right?
Yeah. Well, guys, we can close things down if you'd like. Should we wrap things up? I think we've had a pretty amazing session. The only person that we missed was Greg Hodgin. Again, he had a family emergency. He just wasn't able to make it, and that does happen from time to time. and he promised that he will show up and tell us what's going on with ZC Industries. So for folks who aren't familiar with it, it used to be Zephram Cochrane. I'm not sure if I'm supposed to say that, right? The inventor of the warp drive. He changed the name of it. It's now Zero Carbon Institute, I believe. He is working with a bunch of independent labs, just like folks who present at the APEC conference. Several of them have in the past. And so he has a collection of projects that they are doing, and he was going to give us an overview of that. So I'm hoping to have him back on. And then, we have December already scheduled, and I'm actually got some folks who are interested in coming on in January as well. So, yeah, it's really exciting. And, I just want to personally say, Mark, thank you, sir. Thank you for pulling together last week's lab meetup. Mark moved mountains. He organized, when I saw what he had set up, it was amazing. He organized a pretty vast get-together. We had a ton of people there. We got to test a bunch of different stuff in the vacuum chamber. We did have a couple of little glitches, right? Like Michael's device had some issues with the liquid metal bearing in the vacuum chamber, if I remember right. But overall, it went really, really well. So, Mark, thank you, sir.
And how was the cake?
It was good. It was good.
No one ended up eating that last piece, by the way. Kids didn't want it.
Darn.
It dried out pretty fast, huh?
Yeah. It
Hey,
did.
Mark, that was the 4-year anniversary?
Yep.
Let's do 5 in Florida.
Oh, we could do that. Yeah.
Yeah, well, if we do that, then you're going to have people testing stuff in your vacuum chamber. It'll be a
I'll
madhouse.
clear the decks.
But you have to come to New Jersey first. I came to you.
Man, that's like north of Jacksonville. I don't know about that.
Yeah, I think things went really, really well. I think that was kind of a big conclusion event for the year, although not for all of this, because Jared and Charlie are actually at the Seoul conference right now, and I was hoping that they might pop on and give us an update there, but I guess we'll catch up with them next time and see what's going on. So. Okay, well, guys, why don't we close things down for today then? Thank you all. Thank you all so much. And thank you to our presenters today as well.
Thank you, Tim.
Yeah,
Awesome as usual.
This has been APEC
Right, thanks,
for
Tim.
Saturday, November 23rd, 2024.
Live long and prosper.
We'll have something for you in January, Mark.